Greetings, ladies and gentlemen. Thank you for being here today as well. This is the second day of the 29th Annual Technical Conference and Oil Show and the Technical Paper Conference for Professionals as well. Today we are going to have two sessions divided into two main times. In the first session, we'll be having 4 papers to be presented by today. So heading on towards the first session, we have our chair and the co-chair sitting on the stage. Today, Jawad Ahmed will be acting as the chairman for today's session 1. Mr. Jawad Ahmed is currently working as the director of reservoir engineering at MOL Group, Pakistan. In his academics, he holds a bachelor's degree in petroleum engineering from UET Lahore. He has been associated with oil and gas industry for last 34 years. Prior to joining MOL Pakistan, Mr. Jawad Ahmed has also worked with multiple international and national firms like ENI Pakistan and OGDCL. He has a versatile experience of reservoir management, reserves evaluation, production forecasting, reservoir simulation studies, production enhancement and optimization, field development planning and execution, economic evaluation, production management and planning, production operation, and also has contributed for safe water disposal projects. Joining him by his right side is Saudu Zafar. He will be the co-chair for today's session. Mr. Saudu Zafar is acting as Manager Reservoir Engineering at United Energy Pakistan Limited. He holds a master's degree in petroleum and gas engineering from Norwegian University of Science and Technology. He has been associated with oil and gas industry for last 20 years, having a multi-dimensional experience. Now it times to start the first session and the first paper to be presented by Schlumberger Pakistan. The paper holds a title of Integration of FPWD Technology to Augment Reservoir Characterization. This paper will be presented by Mr. Abdul Bari. He is currently working as the team lead in analytical and interpretation subdivision of DNI. He is covering various domains of formation testing, production logging, well integrity, and perforation. I would request Mr. Abdul Bari to please come on stage for his presentation.
Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. Good morning, ladies and gentlemen. Thank you for attending this session. My name is Abdul Bari, and I am Senior Reservoir Engineer working in SLB Pakistan. And today I am going to present my paper on integration of FPWD, formation pressure while drilling technology, to augment reservoir characterization. These are the co-authors for my paper: Talha Zubair, Mohammad Suhaib Tanveer, Mohammad Rashid Khan, and Zunaira from SLB. Saqib Zaki, Mohammad Jibran, Khizr Saeed, Saad Ali Ghauri from Prime Pakistan, Zaid Ashraf, and Irfan Hamid from OGDCL. Before diving deep into the presentation, let me go through the presentation outline. I'll start with the brief introduction to formation testing, followed by what is formation pressure while drilling technology. Then I will be discussing a little bit in detail about the mud pulse telemetry, which is an integral part of FPWD. Then I will be jumping to the field overview and the downhole challenges faced by the operator in achieving the formation evaluation objectives. Then what we proposed FPWD as a solution. Then I will support this with the case studies, augmenting reservoir characterization. And finally, I will conclude my presentation with acknowledgement and references. So starting with a brief intro to formation testing. We all know formation testing is a technique to determine reservoir pressure, fluid contacts, to determine the fluid type, whether the formation is water bearing, hydrocarbon bearing, and to acquire downhole PVT samples across different depths in a reservoir. This all information is used in completion design, strategy optimization, reserves estimation, reserve simulation model update, and overall field development strategy optimization. So if I talk about FPWD, so FPWD, formation pressure while drilling, revolves around the first two principles of determining reservoir pressure and fluid contacts only. However, if I talk about the advanced while drilling services of evaluation, we have formation sampling while drilling technology as well, in which we can cover the rest of the two applications as well. But since this paper is not covering that scope, so I will be sticking to the FPWD only. So how different FPWD is compared to the conventional wireline formation testers we have. So it's quite similar technique in which we determine the reservoir pressure as well as mobility. However, the tool itself is connected with the drilling BHA with the bit at the bottom, and the mud circulation is continuous. That's the basic difference between the wireline formation testers we have and FPWD. Its applications revolve around the three envelopes of drilling optimization, in which we optimize the drilling efficiency by selecting the optimum mud weight window with knowing the pore pressure. And if I talk about the well placement, we can geosteer the well while drilling to target the sweet spots based on the pressures, fluid gradients, contacts, and samples in case of FSWD, as I said. If I talk about the formation evaluation, so we have fluid identification and contact based on the pressures and the gradients and overall reservoir pressure management. So these all applications are covered by FPWD very well. It's not moving. Okay. Yeah. So let me tell you the key features of FPWD. As I said, the mud circulation is never stopped. So in this case, the cuttings in the wellbore are continuously lifted to the surface, right? And this basically avoids any solid settlement on the low side of the hole. For example, if the hole is highly deviated or horizontal, it will cause solid settlement in the low side of the pipe. And for example, if we are running some tool, it might cause some held up, some drag like this. So the mud circulation helps to remove those cuttings, and they don't allow the settlement of the solids at the low side of the whole pipe, whole section. It can easily be run in highly deviated to horizontal trajectories because we are connected with the drill pipes, and it has less risks involved in case of mechanical or differential stuck situation, as you have maximum pull capacity and your mud circulation is also continuous. And since we are circulating the mud, it helps to lower the downhole temperature. So in case of high temperature to ultra high temperature wells, you can overcome this phenomena, and you can easily acquire the formation pressure objectives. And if I talk about the pretest duration, so most of the pretest types duration, I will be discussing the pretest types in upcoming slides. So most of the pretest types duration is only 5 minutes. And a single pretest at a station depth can take up to 11 to 12 minutes as a whole, starting with the pretest probe setting or retracting, etc. So overall, the stationary time is very limited. So this reduces the sticking probability manifold. As I said, geosteering is one of the applications of FPWD, so you can target the sweet spots based on the pressures, gradients, and fluid mobility data. And in case of challenging and rugged boreholes where your hole is washed out at one axis of the hole, we can always orient our tool to target the shorter axis to increase the probability of getting the seals with the probe, right? So that increases the chances of getting formation pressures in rugged borehole or bad borehole conditions. So now let me tell you how FPWD tool looks like and what are the key features, why this stabilizer blade is like this. So there is a probe at the center and the packer which helps to make contact with the formation itself. And the stabilizer blade is designed in such a way that whatever flow of the mud is, it's not directly against the probe. It is diverted away from the probe. And why it's happening? Because we don't want to erode the packer of the probe, and we don't want to induce excessive supercharging in the pressures. And secondly, we don't want to, erode the packer of the probe. Yeah. So that basically the reason of stabilizer blade mechanism. If I talk about the range of drawdown, you can apply 6,000 to 9,500 PSI drawdown in a single pretest for different tools as we have. And since it has 25 cc chamber capacity with the rate of 0.2 to 2 cc per second rate, so you have variation in the pretest rate and pretest volume, which helps us to get successful pressure measurement in low mobility environments as well, right? And if I talk about this setting piston in blue, that allows for probe set against the formation at any orientation, right? And we have two flow line pressure gauges, quartz and strain. And there is another annular gauge which gives you the hydrodynamic pressure. Why I'm calling it hydrodynamic? Because the fluid is circulating continuously, the wellbore mud. And interesting thing is about the tool power. There is no connection of the tool from the surface through a wire line. The whole power comes from the battery, and there is a turbine in the tool itself, which basically rotates and gives power necessary to run the tool. I will come up with the explanation of mud pulse telemetry in upcoming slide, which basically not only powers up the tool, but it also sends command to the tool and transmits data to the surface from the tool. And if I talk about the pretest types, we have 4 fixed pretest types, 4 time-optimized pretest types, and 4 customizable pretest types. All right? So these are the basically pretest types. As I said, in fixed type, we have 4 types of pretest: 0A, 0B, 0C, and 0D. So these all pretest types, parameters of volume and rate, are designed in such a way to address formation pressure at different mobility environments. So if you are expecting mobility of, let's say, more than 100 millidarcy per centipoise, I will go with the 0D. If I'm expecting more than 10, I will go with the 0C, and likewise. If I talk about 0A, where mobility is very low, you can see that the rate and volume is very limited. And that is why the time taken by this pretest is roughly 20 minutes. However, the rest of the pretests are completed in 5 minutes exact, right? So 5 minutes is the pretest duration, but the pretest probe setting, retracting takes another 5-6 minutes, and that is why, in general, the time estimate is roughly 11 to 12 minutes for a single station. And if I don't know about the formation, and there is heterogeneity in the formation, I can go with the time-optimized pretest. So there are 4 types of time-optimized pretest as well: 1A, 1B, 2C, and 2D, right? So if I talk about 1A, 1B, the investigative pretest has maximum volume of 9.5. However, the rate is variable, right? So if you don't know about the expected pressure, but you know about the mobility somehow, so you can go with maybe 1A, or 1B, depending upon that. If you don't know even about the reservoir pressure, if it's a wildcat well, you don't have any information about the regional pressures, you can go with the 2C and 2D, and it will keep on pretesting until and unless the preceding pretest and the pretest we are doing right now has the same buildup, right? And that is how the measurement pretest parameters are computed by the tool itself, that what will be the suitable volume and what will be the suitable rate to get the representative reservoir pressure and mobility information within 5 minutes, right? So we have carried out all different types of pretest for one of the operators in Pakistan, and we will be discussing in the case studies as well. If I talk about the customized pretest, for those operators for which these all pretest types are not working, they can go with the customized option as well. They do program the pretest parameters, volume and rate at surface before running in hole, right? So that's what happens in the FPWD tool. Now coming to the interesting part of mud pulse telemetry. As I said, this tool is not connected with any wireline or any current source from the surface, unlike conventional wired formation testers. And FPWD tools are connected through mud pulse telemetry. Now, what is mud pulse telemetry? Let me explain you. So in this tool, there is a turbine at the top, and since the mud is circulating inside the drill pipes, moving all the way through this turbine, moving through the tool, and then coming out into the wellbore, right? So this is what happens, and there is a bit at the bottom as well. So when the mud passes through this turbine, it rotates the spinner and it generates power to the tool. That power helps you to run the tool, right? So every pretest type, which I explained in the previous slide, has a characteristic downlink signature. So what happens that we create some oscillations in the mud pumping rate within 10 to 15% range. That creates mud pulses, right? So for example, if I increase the mud pumping rate, it will increase the mud pulse pressure. If I reduce the pumping rate within 10 to 15%, it will reduce the pumping rate. And it will cause a characteristic signature, which we call downlink, right? So every pretest type has a characteristic downlink, right? And as you vary the mud pump rate at the surface, the tool decodes this downlink into whatever pretest type I have selected, and it performs the pretest based on the predefined parameters, right? So this is called downlink. This is how the tool starts taking the pretest. Now, if I talk about how data is transmitted back to surface, so once the tool has this pressure to transmit back to surface, what it will do, it will convert this decimal number into binary digits, right? And there is another tool at the top of this turbine, which we call modulator. In modulator, for just simplification, I have made this hypothetical drawing of stator and rotor. So stator is the static part, and rotor is the rotating part. And it's just like two turbine blades. So what happens that it's basically located right one above each other. Stator is at the bottom and rotor is at the top. And this whole modulator is above the turbine. So what happens? So what happens that if both the blades are misaligned, there will be a back pressure at the top side of this modulator. If both are aligned, there will be negative pressure or there will be no back pressure, you can say, on the top side of this modulator. So if there is a back pressure, this is transformed into a binary digit of 1. If it is a alignment, if it is no back pressure, it will be transformed into binary digit of 0. So we have all these binary digits. The tool will ask modulator to perform this rotor operation in such a way that it completes this binary digits operation, and there is a tool at the surface that decodes these mud pulses and converts it back into the pressure that the tool wants to transmit back to surface. So that is how it works. So the downlink to tell the tool that this pretest type has to be performed, and the modulator operation to transmit data back to surface, right? And it's not single value, it's continuous data. Now let me show you how the data looks like in real time and how the data looks like in the memory pressure data. So the modes of data transmission are two, in real time and the memory pressure. In real time, we can see that the data frequency is slightly limited, but the data is readable. You can QC the pretest. As well as if you see in the memory pressure data, you have more data frequency and you can further QC the pretest. But the pretest pressure difference is not that much high, right? Same is the case for the mobility. Now I'm jumping to what challenges operator was facing in their field. So in multiple fields of the operator, they have multi-layered reservoirs with differential depletion, right? There was a high temperature in one field, roughly 330 to 345 degree Fahrenheit. The drilled holes, some of the drilled wells were affected from the washouts, breakouts, and hole rugosity. And there were some low mobility environments in one of the layers as well. And if I talk about the trajectories, medium to highly deviated, up to 60 degrees. So in order to overcome all these challenges, as I said in the key features of FPWD in the previous slides, FPWD looks to be the fit for purpose solution to achieve the formation pressure evaluation objectives, right? So let me just quickly go through this whole profiling. You can see that it's suffering from the whole washouts and the breakouts showing some kind of tight behavior of the formation. So now, moving towards the first case study. So this is from the first field where the first well version pressure was roughly close to 2100 psi at the center, you can see. And in order to explore this extent of this reservoir, they drilled well 2, 3, 4, 5, and in well 6, based on the BHP survey, they got the pressure of 900 psi, right? And in order to further know the extent of this well, they drilled well 7, but to their surprise, they got the pressure of 2100 psi. So this confirms some kind of compartmentalization of rest of the wells with the well 7. You can see that here is the pressure depth plot. On the left-hand side, we have pressure track, which is close to 2000 to 2200 psi range. Then we have wellbore pressure, mobility information, depth track, and these are the open hole logs, right? So this confirms the reservoir compartmentalization between this well 7 and rest of the wells. If I move to the next, So they drilled another well in the close vicinity of well 7, and they got the pressure of 1650 psi after producing some hydrocarbons from well 7, and that is what adds to their expectation that both the wells are interconnected with each other, which shows that there is a depletion effect in alpha sands, right? Case study 2, which is my last case study. So here what happens, there was a well 1, where the latest BHP survey was showing the pressure of 4490 psi. And on the other side of this minor fault line, the nature of this minor fault line was not known, whether it is sealing, leaking, or partially sealing. So in the well 2, they got the FPWD data, and the pressure was close to 4780 psi. You can see it over here. So this confirms that both the pressures are quite off. So the sealing nature of this minor fault line was confirmed with this. And with this, they got the new prospect area to further recover the hydrocarbons. So that concludes my presentation. Under complex geological settings and challenging downhole environments, operator was successful in getting the formation pressure evaluation objectives. And these presented case studies helped the operator to know the reservoir connectivity, compartmentalization, and the sealing nature of the minor fault line. Thank you. The floor is, so my authors would like to acknowledge the support and contribution from personnel of Prime Pakistan, SLB, Al-Hajj, CUFPEC, and OGDCL in allowing us to publish this work. Thank you so much. The floor is open for questions.
Thank you for the presentation. The floor is now open for the questions. Please introduce yourself and then ask the question. Thank you.
Considering the risk of differential sticking, these probe type tools can be used in those reservoirs because there will be a probe length and then there will be uncertainty of reservoir pressures as well. In northern part of Pakistan, you are not sure about reservoir pressures. If the pressures are lesser than your estimation, then the risk of differential sticking is very high. Should we use these tools in those scenarios? And the other one is, you mentioned the breakouts. How this tool overcome the scenario of breakouts? What is the length of probe which enters into the reservoir? Thank you.
Yeah, very good question. So regarding the first question you said, in case of high differential, although the first remedy is to reduce your stationary time, right? And while doing the pretest with the FPWD, the maximum number of pretest duration is hardly 5 minutes, right? So with only 5 minutes, you get the parameter of pressure and mobility. So this reduces the stationary time. Although we don't have the zero risk of sticking, but the probability of sticking is reduced manifold by reducing the stationary time. That's what we can do. If I talk about the pulling capacity, with the drill pipes, we have maximum pull capacity, right? So that helps you to, apply the pull capacity and release the tool in case of unfortunate stuck pipe situation. Your next question was related to, breakouts, yeah. So in case of breakouts, I'm not going to test those breakout zones, but I'm going to orient my tool to the sweeter spots where I can get representative reservoir pressure and mobility information, right? So based on the image logs, I can orient the tool. I know that at what orientation my breakouts are, so I will set my probe at different orientation. So that is how we can get the pressure.
Shah Jahan from Mol, Pakistan. My question is about the tools reliability. That what is the success ratio of this tool in measuring the pressures? I mean, in clastic, non-clastic formations, and the formations with very low permeability versus formations where you can have like multiple vertical fractures in it.
Yeah, so in case of definitely, in case of near wellbore fractures, you will find difficulty in getting the seal. But the provision of orientation of the tool to the zone where you have, less fractures, it helps you increase the chances of getting seal with the probe, right? Now, coming to the low mobility environment. So we have the pretest types designed for the low mobility as well. And the pretest rate is 0.2 to 2 cc per second, right? So what happens that, how generally the pretest is performed? We take the drawdown from the formation and we allow the pressure to build up, right? So if you take more drawdown, if you take more volume from a high mobile formation, you will have a more chance of getting the reservoir pressure because the formation mobility is good enough and it will build up the pressure at maybe within 5 minutes. But if the mobility is very low, you want to withdraw the fluid volume as low as possible, right? So with the pretest type of 0A, where the mobility range is less than 0.1, we can go with that type. However, the time taken by that test type is relatively higher, roughly 20 minutes. And then we have another option of customizable pretest, where you can customize your pretest volume and rate based on your formation characteristics. Regarding the reliability, with the operator, since last 5 to 7 years, we have been doing these FPWD jobs quite a lot of time in their highly deviated, high temperature, differentially depleted layers. And the success ratio is, you can say, more than 60 to 70%. The operator guys are sitting over here. They can also second. Yeah. And we have got very good pressure measurements in that as well. Yeah.
Just one more question. Thank you.
Abdul Bari Sahir Inam from Mari Petroleum. So I have a couple of questions. One is how different it is from the stethoscope. And the other thing is, normally for the pretest you need open hole logs, and based on the open hole logs you go for any sweet spot for the pretest. In the absence of open hole logs, especially any in the carbonates and thin layers, how you would ensure where I have to take my pressure point?
Yeah, so very good question. So the first question, it is actually the same tool which I am explaining right now over here. It's the same, yeah. So as far as the formation evaluation objectives are concerned, we always need to have the logs first, right? And as I said, there are 3 envelopes of its application. One of them was well placement, in which while drilling the well, whenever you enter the reservoir section, you connect this tool with the drilling BHA, right? And you get the pressure measurement, fluid mobilities, contacts, and in case of FSWD, which is formation sampling while drilling, you can even take the pump outs, you can confirm the fluid type, right? So in case of that, you can geosteer the well while drilling the well, right? So with the formation evaluation objectives in mind, first the operator declares the TD, it acquires the open hole logs, maybe LWD or wireline, and then goes with this run, FPWD run. But you are right that for open hole logs, presence should be there if the objective is formation evaluation, and if the objective is just the casing point determination, you only need the pressure. You can attempt a couple of more pretests to get the reservoir pressure. If the objective is geosteering and you don't have any information about the pressure, then you can just reattempt number of pretests to confirm where I am sitting right now. Yeah.
Thank you very much for the presentation, and we can.
So now we have our second presentation for the first session today, a smart application of acoustic technology to acquire cost-effective surveillance data in brownfields. The presenter is Mohammad Hassan Chaudhry.
So, Assalamu alaikum. This is Mohammad Hassan Chaudhry, currently working with the production engineering and technology team within the subsurface division at United Energy Pakistan, or UEP. Right. So I'll be presenting my paper regarding acoustic survey technology and its smart applications for acquisition of cost-efficient reservoir surveillance data in marginal fields. So let's start with the agenda, which is to have a basic level understanding of the acoustic survey technology and the value addition that it brings to table. This will be followed by the discussion on its interpretation, the equipment, procedural standardization, field data and results. I'll be presenting a case study here, and we'll be closing with some recommendations. So the working principle is pretty simple. A high pressure gas gun is mounted on the wellhead, either on the tubing side or the annular side. The gas gun is basically a small volume chamber with a valve, and it is charged with nitrogen gas at pressure differential to wellhead pressure or casing pressure. When gas is allowed to release in the borehole, it is able to generate acoustic pulse, a pressure pulse that travels down the borehole. And a part of these pulses, when they encounter any restriction or a wellbore anomaly or a diameter anomaly, or eventually the liquid level, a part of these pulses is reflected or echoed back to the surface and is recorded at the microphone, which is part of the gas gun assembly. So these echoes are recorded in the form of amplitude against travel time. Travel time is basically the time taken by the pulse from generation to being eventually recorded back at the surface at the microphone. So we need this travel time. We correlate this travel time with depth, and we'll come to that later in the later slides. So this is followed by the interpretation, where the interpreter mostly selects the right acoustic signal as the liquid level. As you know, there are multiple sorts of informations available on the acoustic trace, and we'll come to that later too. Then the bottom hole pressure is calculated. So the bottom hole pressure is calculated, which is fundamentally the summation of the hydrostatic of liquid column pressure, your gas column pressure, and the wellhead pressure. So the first bit of this, which is the liquid column, the hydrostatic of liquid column, we are using acoustic surveys to determine that. So using this methodology, we are able to get pretty good estimates of bottom hole pressure in a very non-intrusive way. So the value addition that it brings to the table for reservoir and petroleum, for production engineering, the foremost is the faster acquisitions. It's quick, and the campaigns are easier to manage, execute, and plan. Approvals are quick. Quite frankly, we don't even call them approvals now. So you just have to request the field teams for the survey, cutting down the time for the lengthy programs and recommendations. These surveys incur little to no cost, mostly no cost, as there are no consumables involved except for nitrogen gas, which is readily available. And this cuts down the cost of reservoir surveillance, which is particularly relevant in the current context. The results are adequately accurate, and particularly in single and two-phase valves, provided we have a good hold on the interpretation. And I'll be presenting a case study to discuss this further. We have some limitations. There's high error bar, high uncertainties in multi-phase wells, oil wells with a significant portion of water production. The other is its inability to read below the liquid level. So if there's an anomaly, if there's a diameter change, anything you want to see below the liquid level, you cannot see through this. So this is not related to bottom hole pressure estimations, rather more relevant to wellbore integrity investigations, but this is a limitation. Next is in noisy environments, the data acquired is noisy. So if there's a compressor running or a pump running in the background, the background noise on the acoustic trace would make it a lot more difficult to interpret. So this slide is to establish a sense of familiarity with the scale and simplicity of the equipment. On the left, you can see a portable computer, is mostly just this laptop that is used to acquire and digitize the service. With it, you can see a gas gun, and on the right, you can see a gas gun mounted on a wellhead. So within the gas gun assembly, there is a microphone and a pressure transducer. Apart from these, we have some gas cylinders that are used to charge and recharge the gas gun with nitrogen, and some cables. So that's just about it. So diving deep into the details comes the question that how do we correlate travel time with depth? So for depth determination, you need acoustic velocity and travel time. So we are measuring travel time through the acoustic the survey equipment, but we don't have acoustic velocity. And but however, we can calculate acoustic velocities, and there are several ways of that, and I'll be discussing, briefing them one by one. The collar count method foremost is where we identify tubular collars on the acoustic trace, and we count them till the liquid level, and using an average joint length, we calculate the depth, we back calculate the depth and corresponding acoustic velocity. So this is a bit challenging in integral upset tubings, and therefore is seldom used by us. The second method, downhole markers, is the most accurate method by far in our experience. So what happens is that we identify a piece of tubing jewelry on the acoustic trace. For example, we have an SPM in the well, so we see a clear and distinct acoustic signal against each SPM. So if you see the sample acoustic trace, this is from a well with that has about 6 SPMs, and you can see an acoustic signal against each SPM on the acoustic trace. So once these downhole markers, in this case SPM, is defined, it correlates the entire trace with the tele depth of the SPM, and it calculates the acoustic velocity and then depth to liquid level. So method 3 is the average acoustic velocity method, where we calculate acoustic velocity based on gas composition that is prevalent in the wellbore. And there is, however, limitation to this, because there is an assumption that the gas gravity, temperature and pressure conditions would be homogeneous across the whole wellbore, which is obviously not the case. So this is a bit less accurate compared to the other two methods. So we have some parameters that affect the error bar. Gas composition foremost, especially when using the average acoustic velocity method. So an anomalous gas composition analysis would result in inaccurate results, and we would obviously need a representative gas analysis. Similar is the case with the oil and water gravities, which are used for pressure bottom hole pressure calculations, and the incorrect values would result in underestimation or overestimation of bottom hole pressures. The third is the production data, which is more related to multi-phase wells, because acoustic surveys, they cannot detect the oil-water interface within a liquid level. So within a liquid column, your oil-water interface, it has to be determined using the water-oil ratio that is derived from production data that is manually input. So if the production data is not representative, your bottom hole pressure calculations would not be representative. Last is, and most important, is the correct selection of an acoustic signal as the liquid level, because as I also discussed, there are multiple sorts of information available on the acoustic trace. So this mostly comes from experience and the ability of the interpreter. So we standardized the acquisition of these surveys within the organization recently, and to make it more fast and to reduce the approvals time, we did this working back in August 2022, and we put a standardized procedure in place, so such that now we have to just share some relevant, well-related information to the field teams along with a survey request, and the lengthy programs, they're now eliminated because they have a reference procedure with them for execution. So the objective of this was to incentivize the utilization of the acoustic service over memory gauges, because we save a lot of good money substituting acoustic service with gauges. So we have made this acquisition very easy. We have reduced the lead time from request to acquisition from weeks to days. We actually have cases we have requested the field teams to acquire a survey on priority, and we got the data and we interpreted it within a single day. So faster acquisition was one of the objectives. So this also helped us in building our competency in the tool, and this allowed us to explore the tool a lot more. So there came a point we were just acquiring service just because we could. And and at the end of 2022, we saw that we had saved around $45,000 in the reservoir surveillance in just 4 months while substituting gauges with the acoustic service. And by the end of this year, we are seeing this number to be quadrupled. So the plot on the right of the screen, if you can see, the plot tells its story itself. Post-standardization, you can see a significant increase in job frequencies because it was made easy, and obviously this played a very important role in the steep learning curve. So a case study is being presented encompassing of 5 wells from distinct brownfields with varying fluid compositions of each well. So we're comparing the estimated bottom hole pressures from acoustic surveys with the measured data from quartz memory gauges, and the corresponding results are detailed in the slide. We see that, as you can also see, we see an error bar of 1 to 4%, which is, I believe, so fairly acceptable, at least in our case. We saw that the depth correlation method and the fluid type of well, these two were the most significant factors that were influencing the error bar, and downhole marker method, as also discussed earlier, was the most accurate correlation method. But obviously you don't see downhole markers in every acquisition. If there's a liquid level above the downhole marker, you're not going to see it. So lastly, estimation of bottom hole pressures in multi-phase oil wells with significant water production, that results in a higher error bar, higher uncertainties, because the oil water ratio on which the oil water interface is to be defined, that comes from the production data that is manually input. So if we discuss TNE 12 and AX 12 wells here, one of them is a water injector and the other is a gas producer. We see that the difference between the measured and estimated pressures is just 10 psi. So this makes it adequately accurate given the other advantages that it offers. So we would like to share some recommendations regarding the wells in the cases where we actually prefer acoustic service based on our experience and where we don't. So water injectors are mostly always very good candidates. Dry gas wells, we see a very low error bar in gas wells, even with water or condensate production. Oil wells which have no water production, where we can assume the entire liquid column to be composed of oil, these are also very good candidates. We have been shooting a lot of surveys in wells with downhole access issues, where there's a stuck fish, or simply wellbore intervention is not possible, like in the case of coil tubing velocity strings or coil tubing gas lifts, etc. So the next, wells where land access is limited. This is very interesting because we used this a lot last year in August 2022 when the country was hit with devastating floods, and the access to well sites was very limited. So just a pickup is required for carrying the equipment, and the well site access is not to be redressed for heavier vehicles. So this came very handy back then, and we still consider this a plus. So there are cases where a quicker acquisition is preferred over an accurate one. And obviously there are some marginal wells where surveillance otherwise is not justifiable, and we have no cost incurred utilizing acoustic surveys. There are some cases where we actually prefer memory gauges over the surveys. These are, as also already discussed, oil wells with significant water production due to high error bar. And there are some wells that have been long shut in, and there remains an ambiguity in the fluid mix that is currently within the liquid column, right? So obviously the last reported production rates would not be representative of how the liquids have segregated. So next, there are, and obviously there are always some cases where accuracy is paramount and no error bar is acceptable. Like in the case of new wells or very high producers. So I believe so that's about it. If you have some any questions, please shoot.
Please go ahead with questions. Please introduce yourself and then ask the question.
This is Rafiullah from Madi Petroleum. I have a couple of questions. You shown the comparison between the measured and the estimated BHPs. Can you clarify, was it taken at the time when the gauge was hung below, or what was the timing of it? I mean, were it taken at the same time or different times for the comparison?
So in some of the cases, the acquisition and the measurement was done within a single day, in some cases with a few days apart, but not at the same time, because obviously if there's a gauge downhole, that's a restriction and you're going to see it very pronounced on the acoustic trace.
So that could also play a role in the difference in measurement?
I don't believe so. A single day or two, it doesn't make much of a difference.
But considering the low percentage of difference, some part could go to
that could be one of the differences.
One more thing regarding the gas compositional variance you mentioned regarding that. So what's the frequency of gas sampling for accurately estimating it? I mean, because with time there is slight variance in gas composition that we see from fields. So what's your policy or SOP on that for acoustic measurement? What's the planned gas sampling?
So within our organization, gas sampling is done in-house. So what our practice is that prior requesting a survey, we request a gas sample in case we will have to use the average acoustic velocity method. But regardless, the sample that you catch is at surface, and it is not always representative of what is in the borehole. So average acoustic velocity method, we use it only as a last resort if we cannot use any of the methods to correlate.
And just one more question, which is just for learning purpose. The wells where you have multiple side pocket mandrels installed, and if you were to do a annular survey in that, did you see any ambiguity in those, or were it helpful or not, or were there some concerns?
No, actually, when you acquire survey in the annulus, because they are pronounced collars, we actually have two methods available for us, which are fairly accurate for depth correlation. The first would be your downhole markers, because we still see the SPMs on the acoustic trace, and the collars, because then the tool joints, they are very pronounced, and we can count them to the liquid level or whatever we're trying to see in the wellbore, and back calculate acoustic velocity and depth, which is mostly done in a software.
Please, आगे दे दें.
It looks a good technique for when the wells have integrity issues and we cannot take gauges into it. However, if you compare it with the direct measurements we get with the gauges, because as you mentioned, there are some error bar involved, and sometimes we have to take decisions. We need more accuracy, and it may not be used. Plus, it is also based on who is interpreting it, who has, and certainly it is an interpreted data, so it cannot have similar accuracy as of the gauges. So we have to decide on case-to-case basis whether it is acceptable or not, because you will always prefer, because there are so many uncertainties in interpretation, in geology, in material balance calculations, and we are adding another uncertainty in it. So it will be always good to have direct measurement through gauge data, except the cases where we cannot access the downhole.
So, how we see it is any data is better than no data, right? So we have seen a reluctance in reservoir surveillance because of the cost, obviously, in recent context.
I think it was just a comment.
Yeah. Okay.
No need to.
Jawad Sabzwari, Manager Drilling, OGDCL. An academic discussion question. Did you see any, or did you attempt try to make any sensitivity with the frequency of the pulses that you generate at surface, and then you record and see the quality of the data it is able to generate?
Yes, we have done so, although this is not presented in the paper. So the frequency of the pulse is basically dependent on the nitrogen gas charge pressure. For example, if I have a shut-in valid pressure of 100 psi and I have to maintain a differential pressure, so I charge the gas chamber with 300 psi. So there's a 200 psi differential, right? So 200 psi is an intermediate level of a charge pressure. It is not so high and so not so low. We see that where we want to see a restriction or a liquid level at a shallower depth, we keep the differential pressure low. So for example, 50 psi or 100 psi. So that makes the readability more so, because when you fire the shot, there's if you can see at time 0, this is a very big spike. This is a shot that was fired with a higher gas charge pressure, because we knew the liquid level would be below. So we optimize the shots this way, and obviously we have learned it and established this by doing these case sensitivities. Yes. So yeah, exactly. So we share with them the acquisition strategy, which consisting of the number of shots we want, at what gas charge pressures we want, what modes do we want, annular side or casing side or tubing side. So this is the basic data that we now share, and just an email suffices after the procedural standardization, because the rest of the execution steps are covered in that.
Thank you very much for the presentation.
Thank you.
Our third presentation for the first session is titled as Geomechanics Application in North Pakistan, Unlocking Drilling Excellence, a comprehensive analysis of 10 years. Presenter is Shah Jahan from MOL.
Assalamu alaikum and good morning. This is Shah Jahan from MOL, Pakistan. So today I'll be talking about geomechanics application in north of Pakistan, as we are operating in Tull block. We'll be discussing about what led to application of geomechanics in Tull block, what were the challenges, and what we were aiming to achieve out of it, followed by the outcomes and the results, and then the effectiveness of the measures taken. Yes, there were some good things, but there were also learnings from it, which we learned over a period of time, and the purpose of this knowledge sharing session is that any takeaways other companies can get out of it rather than just following the same cycle and repeating the same things. So it's better that we get something out of it. So I'll just start with the challenge description. Obviously, Tal block, as you are aware, is it's in north of Pakistan, and north of Pakistan is known for its typical challenging subsurface as well as surface limitations. So we'll just be talking here about the subsurface challenges. It's a full of localized faults as well as large crossing faults, and then there's a repetition of the formations, which makes it very difficult for the drillers in north of Pakistan to basically get a good efficiency. So in 2014, we basically reviewed all our previous wells data and saw that wellbore instability is one of the biggest challenges that we are facing, and so we have to focus on addressing the wellbore stability related challenges. And it was found to be one of the major contributor in overall drilling efficiency, or you call it drilling inefficiency. So we noticed that every other well that we are drilling, there is a sidetrack in it. Although if you compare our performance with the operators in that region, it was comparably better. But still there was a lot of room opportunity available for us to basically capitalize on by arresting the non-productive time. So as you are aware that total time is basically composed of three elements. One is the productive time, then there is non-productive time, and the tricky one is the invisible lost time. So it's again subjective thing how you calculate the invisible lost time, but at that point in time our focus was that how basically we can reduce the non-productive time, and then it will give us freedom to in next phase to push things as the confidence is built, so that we can then aggressively go and push on the pedal to throttle the thing up. And this is how in the next phase our aim was to reduce the ILT. So just a few pictorial slides of the geological and structural complexities that we have in this area. You can see many faults, high dipping formations, so that leads to lateral heterogeneity. Even if you move like 10 meters, you will get a surprise that you will not find the top of the formation just literally moving by 10 meters. And there is hundreds of meters of difference. That's because of the localized faults and high dipping formations. So another thing is when you compare north with the south, that's the geological certainty part. So one thing that is certain in north is the geological uncertainty. So what we did was that we constructed the geological uncertainty index, basically. I can explain it offline how that was developed, but it was just to substantiate that what was planned and what actually happened there. So that geological uncertainty index was plotted with the excess number of days that we spent from the planned numbers, and there was clearly a direct correlation found that more the geological uncertainty, the higher the non-productive time would be. So this is one of the features that, and I must give credit to our explorationists as well. They are doing their best, but this is sometimes you are planning, this is an actual well, where you planned for 2 repetitions and in actual you encountered 8 repetitions. So on the go you have to survive with the situations. So one more thing that due to these inherent challenges downhole and a lot of problems coming up, one of course because of the regional issues and then the geological uncertainty aspects, that leads to a very high invisible loss time, because when we are drilling we are very cautious that we do not want to accelerate things, and rightly so. If you are drilling fast and there are problems downhole, the control is not good, then you are going to get in a bigger trouble very soon. So first thing first, strengthen your defenses, and that is only possible if you can somehow manage the downhole problems, and then you can come out of your comfort zone to accelerate the things. So you just have to, with the proper risk assessment, thorough risk assessment, this fear of failure has to be taken out of the minds of the teams. It's not working. So let's talk a little bit about the impact on the business for this instability related problem. So it's a global phenomena. In 2009, a report of a journal showed that globally $8 billion are lost due to wellbore instabilities. And in Mole, Pakistan, we noticed that 16% of the NPT at that point in time was due to borehole instability issues. Already touched upon that sidetrack ratio was high, that every other well was being sidetracked. And of course, because of the broken out zones, the enlarged sections, there are other issues, zonal isolation related issues, cementation related issues. So that, I mean, sometimes immediately create problems for you, and sometimes those create problem at the later life of the well, when you have sustained casing annulus pressures and you have to do rig-based P&As. So, other intangible exposures include increased ILT, which is again a subjective thing. One very important thing, and that's a side benefit, and a very big side benefit, is that if you are drilling a hole at a faster pace with a better ROP, you will be getting a smoother hole. If you are spending more time there with high RPMs and low ROP, the profile of the hole will be that such that you will be getting trouble when you are running in hole and pulling out of hole, and you might be mixing it up with downhole instability related aspects. Rather, those tight holes might not have anything to do with the instability, and that sometimes is a misleading thing. So faster ROP is, although it helps in reducing the ILT, also it reduces the confusion that sometimes you mix it up with wellbore instability. So what we did, we carried out an extensive modeling exercise wherein the wells that we have drilled, a thorough post-drill model of all those drilled wells were carried out, and With that, that was populated on a bigger scale and converted it into the 3D models, so that we have a better control about the regional stress distributions and also the explanation of the localized fault. So this provided us better control on our regional lateral properties, mechanical elastic properties, as well as the stress distribution of the region. So once that was done, all the future wells, for the future wells, we were constructing the pre-drill MEM. So that pre-drill MEM worked as the baseline for the planning purposes. These are a few of the graphs of the regional stresses that we were getting in one of the field. On the top left is the regional stress direction, and we've seen that there have been also stress rotations taking place at Lockhart level, which was one of our reservoirs. So this helped in basically identifying the overall orientation, and recently we have also drilled a well where the productivity was enhanced, and we were cutting through the fractures to enhance the productivity. The left picture shows overall stress distribution along laterally as well as with depth, that stress regime is changing from strike slip to the reverse and the normal and vice versa. So it's a very complex region to basically operate in. In few of the previous slides, I showed you that the planned things are not exactly when we drill. The actual scenario is sometimes very much different. So that renders the geomechanic model which is developed at the pre-drill stage ineffective. So if there is a small change in the sequence and the tops of the formations, yes, we have to make the adjustments on the go, looking at the type of cavings that we are getting and the torque and drag trends, and accordingly we can make the mud weight adjustments. But if the changes are significant, there are repetitions and top of the formations are like 500 meter or 1000 meter apart. So this demands that the model, which is now relatively not that effective, that has to be updated. So in order to basically adapt to the situation, this changing situation, and due to geological uncertainty, a pseudo real-time geomechanics approach was followed, that on the go, based on the observation drilling events, T&D, cavings identification, we basically have to update the model, and that was based on the pseudo real-time geomechanics. So this approach also helped us in making the quick fixes to those geological uncertainty related aspects. These are some of the pictures of the different types of cavings. Angular, you find it in the breakout. So if you go through the paper, there's a link to these detailed caving identifications. You can find it there. At the start of our geomechanics application, one of the challenge that we faced was with regards to the platy and tabular cavings. Those were together, those were coming with angular cavings, but these were in a bigger quantity. So these are attributed to the planes of weakness, and this might have a different remedy than the typical breakout caving. So I'll not spend much time over here, but you can go through it. So very quickly, the drilling practices, optimized drilling practices that we followed. this first point is related to those platy cavings, that those are there when we have microfractures and planes of weakness formations are there. So increasing the mud weight is not just the right approach always. So we were using bridging material and microfibers to plug those fractures so that pressure transmission to the wellbore is from the wellbore to the formations is limited. Torque and drag charts were religiously followed for quick proactive measurements. Similarly, against the permeable formations, the static time was reduced, and the availability of contingent LCM through bit LCM availability as well as through PPL LCM availability was ensured. The back rimming was basically avoided. So this is one thing which usually, I mean, the drillers prefer to go on with, but it disturbs the hole. Maybe after the stand down, one can back rim it for a few meters, but it's better that we pump out or to bring it up on elevators. Hole cleaning is essential. Before every connection, pump out 2 to 3 BHA annular volumes, especially when you are drilling in a high ROP environment, which is the area of focus for us. So, in differential sticking or wellbore instability environment, it is recommended to go for one single off bottom. So this particular slide is related to a normal misconception is there in the drilling industry that if we are facing wellbore instability, the only option is that you go for increase in the mud weight. That is not always true. So when you have high overbalance and in the near wellbore region, if the pressures are increased,
excuse me.
So if in the near wellbore region the pressures are increased due to overbalance conditions and the pressure is propagating especially into low permeability fractured formations, then the pore pressure in the near wellbore zone goes up. So as it goes up, the minimum mud weight requirement to avoid the breakouts, that also goes up. So you will increase the mud weight, the minimum mud weight requirement will also go up, unless you put a proper barrier there which is providing a sealing. So that can be done in the microfracture formation with the use of asphalt and sulfatol materials, and that we are doing in our area. So on the right you can see that the shear fracture gradient curve is increasing with the increase in mud weight. So initially that line was on the left and the mud weight requirement was low, and it went up as we drilled without proper treatment, proper sealing. So this slide shows overall results, pre-drill and the post-drill. There was substantial improvement in overall NPT. So NPT is normalized here, expressed in per 1,000 meters. So this was improved. However, the losses related problems increased, and over the period of time we evolved and also addressed on the losses related problem. Sidetracks were drastically reduced, as you can see from the bottom chart, and overall control was improved with the wellbore stability studies. Quickly, last two slides. So on the left is, you can see the performance that is normalized for a 4,000 meter well. Average days spent are on the decline, and even the recent wells that we have drilled, as you can see on the bottom, that X1, the earlier drilled well, NPTs were quite high, and also the on-bottom Rs were also high. So that reflects low on-bottom ROP, and in X2 well, the NPT was significantly reduced, and so was the invisible loss time. Conclusion slide. So overall, geomechanics proved to be very beneficial in reducing the NPT as well as ILT. We encountered multiple failure mechanism here. So based on the type of the failure mechanism, the approach can be slightly different. Bridging helped us in basically closing the fractures and making the increase in mud weight more effective in preventing the breakouts. Caliper logging, that is highly recommended in the non-reservoir sections, that has to be carried out, and expertise in caving identifications, that has to be there with the team. If the caving identification is not right, maybe you will not be able to take the quick reactive measures. Furthermore, various mitigation approaches, you can find it in the paper in detail, so I'll not touch it here. So I think that's pretty much it. I'm ready to take questions.
Thank you so much, Shahjahan. Forum is open now for maximum 2 questions, please.
Bismillah ar-Rahman ar-Rahim. Zaid Ashraf from OGDCL. Definitely drilling in Tal Block, Potoa region is very, very challenging. In pre-drill scenario, how many major problems you was expecting? And actually, how many problems you are reduced from the expected problems? And what drilling time reduced from optimized drilling strategy?
Sir, basically, pre-drill gave us direction that, for example, if the pore pressures in certain formations are going up, maybe the mud weight requirement for those zones was higher. So it is again a subjective thing, but the important thing and about the reliability of the pre-drill models is that when you carry out the post-drill analysis of the offset wells, and if the events, drilling events, cavings, tight spots, LOT or FIT data, that is matching with your post-drill, which is a baseline to develop your pre-drill model. If that is matching like 90% of the time or more, then this gives you a confidence that your pre-drill model is accurate until the prognosed formations comes as per plan. But if the sequence is drastically changed, then of course you can expect deviations from the pre-drill model. And this is all a science of estimation and assumptions. So you can expect, even if the sequences are there, the behavior of the formations can altogether be different. So that's where your reactive approach comes into play. So pre-drill is at proactive level at the planning stage, and at the reactive level is your torque and drag monitoring, your cavings identification, or any tight spots related event. So then you have to adjust it on the go. It's not just that pre-drill is available, we just have to follow it in true spirit, and we have to believe that it will be a 100% solution. No, it will not be a 100% solution. So it will require some dynamism on the go as well.
Yeah, thank you, Shahjahan. I think we can move on to just one question.
Jawad Sabzwari from OGDCL. First of all, I thank you very much, and I congratulate you for presenting your ILTs and NPTs, because people don't usually talk about it. They talk about their successes, but you've been learning through your failures. That is why you're improving, mashallah. My question is that how religiously, I mean, for the sequences that are conforming to the prognosis, how religiously you follow the numbers suggested by the pre-drill MEM studies and WBS, and then you see the results in a post-drill analysis that whether those recommended mud weight ranges were good enough to follow, or you need to recalibrate it after in a post-well analysis. Thank you.
So, very good question. Again, the answer is that we cannot have 100% reliability on the pre-drill model, even if the things comes as are prognosed. So, you prepare for the worst and you hope for the best. Correct? So, you have to have the contingencies in place. You would require a religious monitoring of the drilling events parameters. So, we have to, I mean, if you ask our experience, pre-drill model gives us a baseline. But if we start seeing the contradictions to that at certain mud weight the formations was not supposed to give us trouble and it is giving us trouble, then we deep dive into that. If there are direct indications we are getting angular cavings, we will just without waiting we'll just increase the mud weight to a step change. If there is no risk of losses, formations are competent, maybe that step change is going to be a bigger step change, not a small step change. And meanwhile, we can engage the pseudo real-time geomechanics expert to seek their opinion. So it's always best to get an expert opinion on any matter.
Okay, please go ahead.
Actually, what happens is that we do a pre-drill MEM and prepare a WBS and then just try to follow it, and once it is not complying, then just dump it and continue drilling as per the practices. And what we don't do is this pseudo real-time calibration and the post-well analysis, and that is where we lack actually, and we don't complete the learning curve. And that's what you are doing.
Yeah, yes, totally agree. And just one quick comment with your permission, that sometimes we are taking initiative, and just because you are not seeing that result immediately, or there are some associated drawbacks to that, instead of fixing those drawbacks or those limitations, we say that it's not working, just leave it there. So that should not be the approach, as in my knowledge.
Thank you, Shahjahan. I think we have accumulated sufficient material for tea break discussions. Yeah. So now we can move on to the final paper of this session, please.
Thank you.
So the final paper for this session is scrutinizing the evaluation of heavy sludge formation in situ tar mat problems based on robust integrated PVT and open hole log approach, a case study of an oil field in Pakistan. Our presenter today is Amar Sial.
So, hello everyone, and a very good morning to all of you. I guess it was a kind of then hefty day after listening to much presentations and being at the last. So, I myself, Amar Sial, currently working in Madi Petroleum Company Limited. So, before starting this presentation, let me just give you one example. For suppose a patient is going to the doctor and he tells to the doctor, I have a pain in my hand. So doctor recommends him, okay, do the kind of the diagnostic test. Once he did the diagnostic test, what he found out, actually the pain the cause of the pain was not the hand, but actually it's the elbow. So in our case, doctor or we as engineers, and patient it's actually the field, pain it's actually the sludge, and we need to find out what is the thing which is causing this pain. Moving forward, the topic of my presentation is scrutinization and evaluation of the heavy sludge formation and in situ tar-made problems based on the robust, integrated, and open log approach. Actually, this is the case study of an oil field in Pakistan. The agenda for our today's presentation, we will start with the introduction, followed by the field and background overview. We will then try to cover with the methodology, with the results and the discussion, followed by the conclusion and recommendations. So, well, you know the flow assurance related problems like sludge, oil-water emulsions. This sludge, oil-water emulsions can cause the severe losses in the wellbore. Also it will be difficult to separate them at the surface side. This is the kind of the issue which we were facing. Despite using multiple techniques, heat exchangers, centrifuge, and even the demulsifier at the field, we couldn't be able to break this sludge oil-water emulsion. Failure to break this sludge oil-water emulsion have caused what? Denial by the refinery to accept this crude oil because of its low crude quality. Now, the problem arises, how to tackle this problem? For this, we have gone towards the different literatures to come up with an integrated approach to tackle this problem and to find out the root cause, what is the thing which is causing this sludge. So, moving towards with the field background and field overview, this field was discovered in 2018. It was put on the initial testing in the mid of 2018. After this, it was put on the production in 2019. After some time, it has gone to the significant water breakthrough have occurred. Due to this thing, this field was shut off because we were facing the water disposal issues. After some time, when this field was put online, we surprisingly here we were facing the sludge issues. Now the objective is to find out the root cause of this sludge and oil water emulsion and to see whether the sludge and oil water emulsion is actually happening in the reservoir or at the wellbore. The outcome of this whole study have helped us in the proper screening of a demulsifier. Secondly, it has kind of provide us a diagnostic approach which we can implement it for our future oil field where we will face this kind of the issue. So now to go with the kind of the diagnostic which we have come across, we have used and multiple kind of the techniques to merge them to call it as an integrated workflow. First, to start with the PVT data evaluation, in which the PVT data was analyzed, gas chromatographic results were evaluated, followed by the different reservoir parameters were evaluated. These two approaches have told us regarding whether the sludge oil water emulsion is actually forming because of the biodegradation or it might have the other issue. After this, we have used an auxiliary approach. This auxiliary approach was based on the three different approaches. First one was the colloidal instability index, which can tell the colloidal instability of the asphaltene based on the various ranges. Below 0.7 shows the stable region. If the value lies between 0.7 to 0.9, it will indicate an uncertain region. If this value is greater than 0.9, it will show us an unstable region for the asphaltene dropout. Secondly, de Boer method was chosen. It's a kind of the diagnostic plot. which is used to check if the asphaltene dropout is occurring or not, along with the resins to asphaltene approach, was also used for showing the variations in the resins, resin to asphaltene ratios. After this, to check if this sludge is occurring because of the presence of the in situ tar mat, which is actually existing within the reservoir, to evaluate this thing, open hole log and mud log logs were analyzed and evaluated. After this, to check this sludge and oil water emulsion, it's happening because of the salt. For this purpose, water analysis approach was also done. To further revalidate and confirm the results of all of these approaches, we have used an PVT wellbore hydraulics molding approach to confirm the results of all of these approaches. Moving towards the results, well, first thing to see what is the thing which is causing the sludge and oil water emulsion issue. First thing is to analyze whether the sludge and oil water emulsion is happening because of the biodegradation or not. For this thing, PVT data was evaluated and analyzed. Here, it shows the gas chromatographic result of one of the valid bottom hole sample. From here, we can see the whole chain of the N-alkanes and isoprenoids are intact, which is kind of similar to the unbiodegraded samples. Meanwhile, here the C chain, C7 chain, is higher compared to the others, which indirectly indicates the presence of the resins here. To further revalidate this thing, whether this oil is not biodegraded, the different reservoir parameters were also evaluated, and it's compared with the different threshold values. Based on the comparison, what we have found out, there was no biodegradation was occurring based on the reservoir parameters. Meanwhile, there is the presence of the sludge and oil water emulsion based on the GOR and sulfur wax content. So the chances of the oil water emulsion is mainly due to here the flow assurance issue, not because of the biodegradation. So first diagnostic we done. Now to see what are the other things which is causing the sludge and oil water emulsions. For this, asphaltene and resins dropout were also evaluated, and their contribution was also analyzed based on the auxiliary approach. For this, we have used the 4 approaches: SARA, colloidal instability index, resin to asphaltene ratio within this approach, de Boer approach, and the asphaltene onset pressure. From the SARA, what we found out, the resins has been increased while asphaltenes has been decreased. To further evaluate this thing, the colloidal instability index was also evaluated, which indicates this colloidal instability index have been decreased from 1.83 to 1.51. Meanwhile, the resin to asphaltene ratio has been increased from 0.9 to 2.75, showing the significant resins increment. To check the asphaltene dropout, de Boer approach was used. Based on this, the operating conditions were put on the global de Boer plot. Based on this thing, no asphaltene dropout problems were identified. Meanwhile, asphaltene onset pressures were also evaluated, which indicated that these asphaltenes were dropping out at a very low pressure of 1015 psi. So from this thing, what we found out, there is no oil biodegradation. Second, this sludge and oil water emulsion, it's actually happening because of the resins, not because of the asphaltenes, which we were targeting at the field site using the demulsifier. Now the third thing is to check whether the sludge and oil water emulsion, it's forming because of the in situ tar mat. For this thing, we have used an mud log and open hole log approach. For this thing, we have used the Pearson approach, which is based on the wetness, balanced, and character ratio. What we have found out, if this WH ratio increases, it will indicate the different types of the hydrocarbon exist within the reservoir. This is the same type of the data which you are getting from the mud log. This approach we have used to qualitatively determine the compositional gradient exists within the reservoir. What we found out? Based on this WH ratio, our crude oil lies in the medium category, and the WH ratio is continuously decreasing. No significant compositional gradient exists based on the gas ratio approach. Meanwhile, no in situ tar mates were also identified based on the open hole log approach. No biodegradation, resins issue, no in situ tar mates. Now, fourth thing is to see if this sludge and oil water emulsion is happening because of the salt or not. For this, we have used a water analysis approach. What we found out, low value of the tan of 0.25, decrease of the pH from 6.5 to 6.2, and high content of the calcium increase and decrease of the sodium content indicate the presence of the calcium naphthanates exists in this sludge and oil water emulsion. So this might be the one which can also contribute to this strong formation of this oil water emulsions. Finally, to confirm these things, we have used an PVT and wellbore hydraulics molding approach. The equation of the state was matched, and based on this equation of the state matched, we have generated the compositional gradient exists within the reservoir. What we found out, there was no significant increase of the compositional gradient, as there was no change in the components, in the components, GOR, density, and the API was observed. This approach is actually we are using to revalidate the results which we have found out from the previous 4 to 5 approaches. To further evaluate, salt mapping was also done based on the PVT matched modeling. What we found out, around 34 to 40% of the salt will be precipitated out at the reservoir pressure and surface pressure, while 59 to 62% of the salts will remain in the solution. No wax issue has been identified based on the current approach. Around 96% of the wax will remain in the solution. To further evaluate the asphaltene dropout issue, we have used the wellbore hydraulics modeling approach, in which what we found out, the asphaltene flakes were appearing at a very low rate, indicating that there is no issue of the asphaltene dropout at this current operating conditions. So, to conclude this thing, we have used 5 to 6 approaches. These 4 to 5 approaches, we have validated them with the PVT molding approach. What we found out, resin is actually the one who is contributing to this strong sludge formation, which we aren't able to break at the field site. Secondly, resin-based demulsifier must be chosen, which will target the resins instead of the asphaltene. No in situ tar mates have been identified. No asphaltene and wax issues have also been identified. And the main root cause of this heavy sludge, it's actually the calcium naphthanates, resins, and no significant compositional gradient exists within the reservoir. Based on all of these results, we have gone for the way forward was we have chosen the demulsifier, which was based on the resin, and it has targeted the sludge, which was significantly improved to the which has been significantly decreased to the certain level. Still the injection trial is continuing, and if there is an issue of the naphthanates, we will recommend to use the acetic acid, which will target this calcium-based naphthanates. For further validation, if someone wants to do it, they can do the bottom hole sampling approach to determine whether if the composition gradient exists or not, because this is based on the qualitative approach for finding the compositional gradient when you don't have the bottom hole samples at the various depths. So we would like to thanks to Madi Petroleum Company Limited for their permission to publish and present this work. Special thanks to Reservoir Department for their support and revision throughout this process. These are the references, and thank you so much for listening.
Ji, please go ahead with the questions.
Bismillah Rahman Rahim. How you integrate PSP results for compositional gradient and any other data?
Can you repeat your questions again?
How you integrate PSP results for compositional gradient?
PSP results, actually the PSP will only indicate you the wellbore phenomenon, not to the reservoir, because it's the extent of its investigation, it's smaller. But what we have used here, actually, because we don't have an MDT data, we try to correlate it simply with the PSP based on the gas ratios. Gas ratio, what we have found out here, no significant increase of the WH. It was continuously decreasing. This thing, we have further validated it with our PVT modeling, which also indicates no composition gradient exists. If at this particular depth, there was the existence of the composition gradient, we could have seen it. But with this particular interval, no existence of the composition gradient. And this can also be verified if indirectly, if you want to verify it with the PSP, because the in situ density, if it's same, then it will indicate there is no change of the density exist here.
So you used only gas entry points from the PSP?
No, let me clarify. We have used the gas ratio approach and try to verify this gas ratio approach with our PVT modeling. From the meshed PVT modeling, we have generated an EOS, equation of state. From this meshed equation of state, we have tried to generate the composition gradient at this particular interval. Thank you so much.
Okay, thank you.
I'm Vakar from PPL. From the study, you have concluded that the problem is due to the calcium naphthenes, I guess. And the solution you are providing that you need HCl to resolve this issue, if I elaborated correctly.
The thing, let me clarify again. For the resins, we are recommending to use the demulsifier, which will target the resins only, not to the asphaltene. Because at the field side, we were using the demulsifier, which was targeting the asphaltene, which wasn't breaking the emulsion. But with this process, what we found out, there is also the issue of the calcium naphthenides. With the different published data and with the published field trials, they recommend to treat this calcium naphthenides, it's better to use the acetic acid.
So have you applied this technique on this problem and you have?
No, currently the field trial is going on and we are getting very good results as well. But it will be improved with the time to time.
But the problem is resolved only with the resins based
yeah, it has significantly decreased, yes.
Okay, thank you. Thank you.
Assalamu alaikum. I think it's a very good paper, and you have highlighted the issues which mostly the industry is not very much well taken care of. My question is that in the absence of the subsurface samples, probably there would be an issue that your asphaltenes or resins would have been dropped in the reservoir or in the wellbore. And looking at your data, you're looking at the reservoir pressures you have and looking at the APIs you are having, and I think the productivity is at the very lower side. Probably KH would be an issue. Have you ever tried to go into the wellbore and see by bottom tagging the see the clearance of the whole wellbore that you have any issues of these asphaltenes or these what you just saw, like sludge, something in the wellbore? And have you tried to rectify this at the subsurface level?
Well, to answer this thing, thank you so much. It's a very good question. Firstly, yes, there will be the asphaltene dropout because based on the asphaltene onset pressure, it's around 1015 psi where you have the maximum asphaltene dropout. So you will have an asphaltene dropout at the wellbore. But when it comes to the surface, it's not the problem of the asphaltene we are facing here. It's the sludge. You have the water, you have this kind of the biscuit, which we are calling it the sludge, and above it, it's the oil. We want to remove this biscuit because it's at 30% of the oil, it's around contributing to 35 to 50% of this oil, which is forming as the form of sludge. The problem, if we were facing the asphaltene issues, we would have treated them with the demulsifier. But I'm telling you, we have used multiple techniques. None of them were able to remove this sludge. None of them able to break this sludge. For the asphaltene, if you are hitting them too much, it will degrade. It can't return back to the liquid. But here, it's not the asphaltene, it's a sludge.
So have you tried going to the wellbore and see that there is no asphaltene or any?
Yes,
kind of
we have verified it with the wellbore hydraulics molding approach. We have on all the scale flags, and if there was the asphaltene formation, it could have shown us. But what I have shown here, there is no asphaltene scale based on the current conditions, based on the current operating conditions.
So
okay,
I think we should
thank you so much.
Conclude the session. We have already run half an hour over, I guess. Amar, thank you for your detailed presentation. Hope a few questions can be, or you can discuss during the tea break. Now we come to the conclusion of this session. Jawad sir. Okay, so now the session is, first morning session is formally closed now.
Thank you so much.
Thank you to all the presenters for such innovative and thought-provoking papers to be presented in this session today. Now it's time to give them the shields as a little token of appreciation for their hard work. The shields will be presented to the authors and the co-authors of all the papers, and this will be aligned as the presentation numbers were. So the first paper presented today in this session was Integration of FPWD Technology to Augment Reservoir Characterization. Papers were presented by Unexplored Pakistan team. I would like to request both chairman and the co-chair to please move forward for the presentation of for presenting the shields to the authors and the co-authors of each paper. I would like to request Abdul Bari, the author and the presenter of the paper. Followed by him would be Saqib Zaki, Muhammad Jabran, Khizar Saeed, and Saad Ali Gori. The second paper presented today was Smart Application of Acoustic Technology to Acquire Cost-Effective Surveillance Data in Brownfields. The paper was worked on and presented by United Energy Pakistan Limited's team. I would like to request Muhammad Hassan Chaudhry, the presenter and the main author of the paper, to please come forward and receive its shield. Followed by him would be Hafiz Muhammad Arsalanullah, Mr. Fawzan Iqbal, Zaim Hassan Khan, and Rahil Ahmed. In case of absence of all the co-authors, I would like to request Mr. Hassan Chaudhry to please receive their shields as well. The third paper presented today was Geomechanics Application in the North of Pakistan, Unlocking Drilling Excellence, a comprehensive analysis of 10 years. The paper was worked on and presented by MOL Group Pakistan. I would like to request Shah Jahan Khan, the main author and the presenter of the paper, to come forward and receive the shield. Followed by him will be Ahmed Nawaz Awan as the co-author of the paper, to please come forward and receive the shield. The last paper presented today in the session 1 was synchronization of evaluation of heavy sludge formation and in-situ tar mat problems based on robust integrated PVT and open hole logging approach, a case study of an oil field in Pakistan. The paper was worked on upon by Mari Petroleum Company Limited. I would like to request Mr. Amar Syal as the main author and the presenter of the paper to please come forward and receive its shield. Followed by him will be Muhammad Aftab Solanki as the co-author of the paper to please come forward on stage. Munib Ali Virk. Mr. Ali Hamid. Mr. Nadir Amin. After the ending of the presentation and presenting the shields to the authors and co-authors, now it's time to present the shields to the chairman and the co-chair for today's session. I would like to request Sayyid Shariq Ali Hashmi to please come forward to the stage and present the shields to the chairman and the co-chair of today's session. The first session for today was chaired by Jawad Ahmed. And the co-chairman being Saudo Zafar. Thank you, Chairman and the co-chair, for their presence on stage. Now it's the end of the first session for today. I would like to request all the audience sitting here to please stretch a little and grab the refreshment and be back on time for the session 2 after half an hour. Welcome again, everyone. I hope you have got stretched and had got your refreshment. Now it's time to start the last session for these 2 days campaign. This is the session 2 for today's presentations, and 4 papers will be presented in the session. The session will be chaired by Mr. Saeed Akhtar. Mr. Saeed Akhtar is currently acting as a General Manager, Reservoir and Petroleum Engineering at Orium Petroleum. He holds a BS degree in Petroleum Engineering from UET Lahore. He has been associated with oil and gas industry for last 32 years. Having a diversified experience in reservoir management, reservoir simulation, asset evaluation, techno-economic analysis, field development, its planning, well testing, production optimization, and well operations. Prior to joining OPI, Mr. Saeed has also worked with multiple companies like OGDCL, POL, GHPL, PEL, Divan Petroleum, and Spud Energy Private Limited as well. I would like to request Mr. Saeed Akhtar to please come on stage. Joining him as the co-chair for this session will be Fahim Razak Awan. Mr. Fahim Razak Awan is currently working as a manager reservoir management at Mari Petroleum Company Limited. He is mainly responsible for the asset management of Mari gas field, which is the largest gas producing field in Pakistan. He holds a master's degree in petroleum engineering from Hertford University, UK, and an undergrad degree from NUS University as a mechanical engineer. He has been associated with oil and gas industry for last 2 decades with his expertise in integrated reservoir studies, asset management, enhanced oil recoveries, reserves evaluation, reservoir performance, its prediction, project management, and production optimization. Prior to joining Mari Petroleum, Mr. Fahim Razak Awan has a diversified experience while working for prominent organizations such as Halliburton, Talisman Energy UK, Repsol Sinopec UK, and Apache North Sea UK. His contributions has been instrumental in extending the life of the field and maximizing recovery from major North Sea oil fields, including Piper, Forties, Claymore, and Tartan. I would like to request Mr. Fahim Razak Awan to please join as co-chair for this session today. In this session, as I have mentioned before, 4 papers will be presented. So the first paper which will be presented today will be by Sprint Pakistan, and the title for the paper is High Rate, High Volume, a novel technique for uniform metric stimulation of naturally fractured low pressure reservoirs. Paper will be presented by Harun Rashid. I will request Mr. Harun Rashid to please come on stage for this presentation.
Hello everyone. My name is Harun Rashid. I'm working as senior engineer, coil tubing and stimulation in Sprint Oil and Gas. As by the name of the topic, I'm going to present a novel technique, high rate, high volume, as a metric stimulation technique in low pressure naturally fractured reservoirs. It is actually a case study in which we have utilized this technique and get most optimized results. Since this technique was kind of a modification in upcoming wells, we have performed conventional technique in the previous wells but didn't got results as we were expecting. But with this modification of utilizing this high rate, high volume technique, we got multiple folds of increment in the production. So the objective of this presenting this paper is we have naturally fractured reservoirs which like the depleted fields or the low pressure reservoirs in Pakistan as well, where we are utilizing conventional techniques. So we need to focus on the data where we are utilizing the conventional techniques and need to switch towards this new technique to get optimized results in terms of production. This is the flow of presentation. First, we'll see the objective of metric stimulation and the challenges we face in low pressure reservoirs. Secondly, we'll see the different asset placement techniques. Then we'll see the details of the case study in which we'll compare the job execution, stimulation results, job execution graphs, and the post-job results we got from both of the offset well data and the wells after utilizing the modified technique. The objective of metric stimulation is to mitigate the pressure drop arises due to skin to increase the productivity of the well. The metric stimulation technique gets a challenging technique when we are performing it in naturally fractured low pressure reservoirs. Since there, if we have, and it gets more challenging when we have high permeable zones in terms of heterogeneity and the permeability of the different streaks in the reservoir. So that high permeable zone acts as a loss zone and gets the injectivity of all of the treatment fluid in it without going into the low permeable zone, which jeopardizes the objective of the treatment metric stimulation job. So what we need to do is to divert this the treatment fluid of lossing in the high permeable zones, and it needs to go into the low permeable zone. So we need to divert this treatment fluid. For this diversion, we have different asset placement techniques. First, we can use a mechanical technique by utilizing a bridge plug or any kind of packer or combination of both, by which we can plug the high permeable zones and then pump or inject the treatment fluid into the low permeable zones. Another one is the coil tubing, where we can place acid at our desired depth. Also, we can utilize different kind of BHAs for which for different depth of penetration as well. With this technique, we can have a safety factor as well, by which we can say by hindering the flow, the treatment fluid by avoiding the contact of treatment fluid with the completion. Next one is the ball sealers, in which we pump cylindrical shaped small balls made up of solid nitrile coated with aluminum in the well, which resides in the perforation tunnel, and divert the upcoming fluids towards the low permeable zones. After that, we have chemical diversion and the foam-based diversion. The chemical diversion involves the changes in the chemical properties of the treatment fluid, like viscosity. We can increase the viscosity of the fluid, by which when it gets injected into the high permeable zone, it provides hindrance to the upcoming fluid, and the upcoming fluid can get injected into can go to the lower permeable zone. Foaming technique is similar to the chemical diversion technique, where we introduce a foaming agent in our treatment fluid, and that foam, which creates the treatment fluid, which creates a foam type mixture of the treatment fluid, and that foam has high surface area. That surface area is going to provide hindrance for the injection of the fluid in the high permeable zone, and the upcoming fluid can go to the low permeable zones. The last one is the high rate, high volume technique, which we are presenting. Is in high rate, high volume technique, we inject the fluid at rates above the injection rate of the permeable zones, so that it can provide a scenario like a bottleneck, where we are injecting the fluid in the high permeable zone, and it goes to the low permeable. The upcoming fluid can go to the low permeable zones. Now we'll see the details of the case study, in which first we'll see the fluid selection, that how we have selected the treatment fluid for the metric stimulation job, which consists of two laboratory tests. First is the solubility test, and second one is the reactivity test. In solubility test, we have performed tests with the formation cuttings in two acid systems. The fluid selection for the formation cuttings sample was considering limestone, so it was HCl based acid system, and we have performed two tests with two concentrations, HCl 7.5% and HCl 15%. We get good solubility results in both of the acid systems. 7.5% was giving around 75 to 80%, and 15% was giving around 80 to 85%. Moving on towards the reactivity test, the reaction in 15% was more vigorous than the 7.5. Considering less than 200 degree Fahrenheit temperature, reservoir temperature, we have considered 15% as our treatment fluid. We can opt for more concentration, but since to avoid any damage to the completion jewelry, since the well was old, so we have opted 15% HCl. Now we'll go through the details of the case study, the job execution. We have performed 2 jobs utilizing different divergent techniques, as we have discussed before. First, we have utilized foam-based technique, in which we have pumped the treatment fluid at 5.5 barrels per minute, achieving an injection rate less than 500 psi. The graph is showing that stable pressure is showing that most of the treatment fluid was got lost in the thief zone. Similarly, in the next well, we have utilized kind of an improvement to use the chemical divergent technique as well, by the combination of both, but the similar results were achieved, like the injection pressure was less than 500 again, and most of the fluids got lost in the permeable zone. So we decided to move on further, and we have utilized the foaming agent technique, we have utilized the chemical divergent technique. What we can do is to increase the rate, and we have performed multiple simulations and achieved different invasion profiles, calibrated our simulation results with different data points, and got the simulation results of the well. So in the next well, we have performed simulation at high rate as well with chemical divergent, and low rate with chemical divergent. You can see on the graph on right side, the invasion, as the invasion profile shows that most of the fluid is getting injected into the shallower zone of the reservoir, and when we that is the invasion we are getting with low pumping rates. When we have increased the pumping rates near to more than 25 barrels per minute, then we got the invasion. As you can see that it is nearly uniform, and the fluid is going through all the streaks of the reservoir. One thing we noticed during increasing the rate was the factor of friction factor. As we were increasing the rate, friction losses were increasing as well. What we needed was to achieve high bottom hole injection pressure actually. So as we were increasing the rate, we were not getting the increment in the bottom hole pressure, but the increment was in the friction losses. So to mitigate or to minimize this factor, we have utilized friction reducer as well. So we have performed an injectivity test with 4% ammonium chloride brine, and achieved 25 barrels per minute at around 3000 psi. This was the limitation set by the client for the surface equipment, and this was the rate we have achieved. And we have performed similar job on the similar rates and got increment in the production up to 3-folds. Like the well was producing previously at 1 million, and then it increases to up to 3 million. We have performed a similar job on another well where we have achieved an injection rate of up to 40 barrels per minute at 3200 psi. And the job was performed in a similar way with the combination of chemical diversion, and we achieved the increment in the production up to 3-folds. What we have done in both of these wells was the introduction of a pad fluid as well, a viscous fluid ahead of the treatment fluid, which get injected into the permeable zone first, which provides the hindrance to the previous upcoming fluid. And that fluid is also going to be injected at high rate, the rate at which is the more than the injection rate of the permeable zone. So this is the combination of different divergent techniques by which we have achieved these optimized results. And then we have lesson learned and conclusion. Like what we have learned is we have tried in 2 or 3 chemical divergent. First we have tried chemical divergent technique. Second we have utilized first we have foaming technique. Then we have chemical divergent technique. Then we have utilized the different combination of divergent techniques, which includes the high rate high volume, which is the dominating divergent technique in the case studies. So combination of these chemical diversion and the high rate, high volume technique provides better results. Second lesson learned was that the data from the offset well has significant importance, since what we were doing we were using the data and simulating the invasion profiles by which we get the optimized results. So analyzing the data and the data set of the offset wells is a critical point as well. Also in achieving the high rate, the major factor hindrance in doing the high rate, high volume job is the friction losses we are encountering during achieving the high rate, and use of friction reducer in those treatment fluids gives us a decrement of 20% in the friction losses. In the last, I would like to thank my colleagues and my fellow seniors to providing me this opportunity to present this paper, and thank you all of you to spare your time and attend this session. Thank you so much. If you have any questions, you are more than welcome, please.
Thank you, Arun. Now the floor is open for the questions.
Assalamu alaikum. Mohsin from OPI. I have a question. You mentioned in your slides limestone formation.
Yes.
So what was the matrix porosity?
Metric porosity was around, to be honest, I'm afraid I can share this data or not since it's the client data, but it was around near to 20%.
Oh, 20%. So what kind of viscous fluid you used in this technique for diverging? Is polymeric gels or?
Yes, what we have used was West-based viscoelastic surfactants that has a kind of an amphoteric surfactants which gets viscous when the acid reacts with the formation material. Like it depends on the pH and on the chloride content. It depends on different properties. Like we can make it viscous by adding it in the HCl-based acid system, and when it gets react with the calcium carbonate, the pH is going to get increased. This increment in the pH is changing the properties of the fluid, and the fluid is going to be viscous. Also, this fluid, this West-based chemical diversion is non-damaging as well. It gets break when it comes in the contact with the hydrocarbons.
Okay, thank you.
I got one question. Was there any consideration for the frac pressure?
Frac pressure was around, I've shown in the...
Especially at the higher rates, what was your bottom hole pressure? How does that compare with the fracture pressure?
It was around 4,500 psi, 4,000 to 4,500 psi, but we were not able to achieve the fracture pressure. Since by increasing the rate, we were achieving the surface limitation, and that surface limitation major portion of that surface pressure was the friction losses. So we were not getting the bottom hole pressure equal to or near to the fracture pressure. Yes, we can achieve the fracture pressure, but we need to reduce the friction losses.
Okay, any more questions? Okay, one more, last question.
Yes.
Harun, thank you for the great presentation. Are these jobs performed in the cased hole or open hole?
Both of those jobs were performed in a slotted liner.
Okay, thank you, Harun. Very good presentation.
Thank you so much. Thank you all.
Very much. Okay, the next paper is on the role of temperature on the performance of in situ CO2 EOR, and the presenter is Saddam Hussain.
Assalamu alaikum everyone. Thank you. The title of my presentation is The Role of Temperature on the Performance of In situ CO2. I'm associated with United Energy Pakistan as Reservoir Engineer for South Indus Asset. The agenda after my presentation is I'll be briefly touch upon the in situ CO2 evaluation, the technology, and the objective of our study. And I'll be discussing or explaining the reaction kinetics and then I'll be jumping to the Gibbs free energy, and then mainly I'll be discussing the numerical modeling of numerical modeling of a 1D lab model and a 3D model, and then some sensitivity analysis on the temperature, and then the key outcomes and the acknowledgement. Since we all know that the supercritical CO2 is globally well known as an EOR method, but there are certain challenges involved in the supercritical CO2 injection, such as the transportation and the high capex involved for the infrastructure, and more importantly, we need the abundant source of CO2 for injection purposes, and all of these requires high capital expenditure, such as like mainly if we are talking about the market like Pakistan, we don't have the more abundant CO2 sources. We require like high pipeline. If the CO2 source is like very distant, we require morely like very large pipelines, and then it will also require the infrastructure such as compression cost and the surface facility cost. But how to overcome these challenges? So the latest technique of in situ CO2, where we are generating the CO2 inside the subsurface by injecting some CO2 generating chemicals such as urea. There are some other chemicals, but for our case, we are utilizing the urea, which is a byproduct of ammonium carbamate. And then in the urea reaction, you can see that this is the urea, and then once it reacts hydrolysis, and then it generates ammonia and the CO2 inside in the subsurface. There are some kinetics involved with this reaction. Once this reaction is spontaneous, it's going to contact with the oil. Once it's contact with the oil, all of the CO2 that is generated inside the reservoir, it kind of partitions or dissolved into the oil, and then the ammonia, that is another byproduct of this urea reaction, it generates the in situ surfactant in the reservoir. So there are two synergetic mechanisms, mainly two synergetic mechanisms that are involved in this kind of EOR technique. One is once the CO2 is partitioned into the oil, it swells the oil and reduces its viscosity, which even in the end it will increase the mobility of the oil and kind of also reduce the interfacial tension by mobiling the capillary trapped oil. And another added synergetic mechanism of this technique is the wettability alteration by generation of in situ surfactant with the help of ammonia. So the objective of this study, we evaluated the reaction kinetics, how does the urea behaves under certain pressure and temperature condition, how the urea reaction is impacted by different temperature conditions, and then the different chemical models that are built to evaluate the chemical potential of the urea in order to see at what temperature the urea will be spontaneous. It's going to generate the CO2 and ammonia. On the second side, and after that, after evaluating the urea reaction kinetics, we history matched our 1D lab models. There was some core flood experiments available, so we history matched that models and then upscaled our 1D model to the 3D model with the help of by building a quarter 5 spot model, and then see in order to evaluate how does this technique behaves under a subsurface environment at different urea concentrations and different injection rates and different injection temperatures. And at the end, we ran some sensitivity analysis on the temperature by keeping the objective function of maximum recovery that we can get with the lesser urea injection. So in order to evaluate this technique, we need to understand its kinetics first. And for the first thing is how does the CO2 is behaving or partitioning into the oil. That is based on the partitioning coefficient. We all know that the CO2 once it injects in the subsurface at higher pressures, it more like behaves like a liquid and its density becomes higher. So once the CO2 is generated under the reservoir condition, and then this CO2 is going to partition into the oleic phase or the oil phase at reservoir conditions. And then this partitioning oil will become swell and will reduce the viscosity. And the reaction kinetics, we computed the reaction kinetics based on the Arrhenius model, and there were some previous researchers who worked. They worked on the reaction kinetics of the urea, such as Kai et al., Sahu, and some other researchers who computed the reaction kinetics at different reservoir at different temperatures. And we see that the higher the temperature, the higher the urea reaction kinetic is. So in order to evaluate that what will be our temperature envelope for different reservoir conditions, like at different viscosities, different temperature conditions, how does this urea is going to behave under in terms of the simulation. But because in the analytical working, it shows that the higher the temperature, higher are going to be the reaction kinetics of the urea. So you can see that at the table below, these are the activation energy and the pre-exponential factor that were computed by different researchers at different temperature conditions. You see that at the higher temperatures, like 140 and 300, you see that the activation energy becomes very high. And once the activation energy becomes very high, since this urea hydrolysis reaction is an exothermic reaction, and it kind of evolves like all of the heat into the system. So after that we computed the Gibbs-free energy of the reaction, because this is going to tell us the chemical potential of the reaction, because we must know that at what temperature this reaction is going to be activated or this reaction is going to be spontaneous. So it is the Gibbs-free energy model that gives us the direction of the reaction. And in this model, it tells us the change of enthalpy and entropy of the reaction of the reactants and the products. And once the Gibbs-free energy of the reactants is become greater than the reaction energy Gibbs-free energy of the products, the reaction is become spontaneous. And on the right hand side, you see this picture. It shows that at the almost 70 degrees Celsius, this reaction is become spontaneous. So after that, once we increase the temperature, this reaction is going to be higher and higher, and we will have more and more CO2 into our reservoir. So after that we history matched the 1D model. We estimated the 1D model. There were some core fluids available, and these core fluids were based on the post water injection. And you see that this is the residual oil saturation after water injection, and the residual oil water saturation was around 28%. We injected around 8 pore volumes of the brine in urea in different intervals. Like you see here, initially you see there is a small reduction in the residual oil saturation. That is because we injected the urea at this interval, and then after that we shut the injection valve in order to react the urea more and more into the reservoir and generate the CO2. And then after that, after the almost 3.5 pore volumes, once we opened the producer valve or the producer or the outlet side of the core, we said there is a lot of oil production. So what we concluded is that there were different kind of these synergetic mechanisms that were involved, but the problem was we could not get the history made based on the reaction kinetics that were previously evaluated by different researchers. So that was another key challenge, and we modified the reaction kinetics in order to get the history match. So that was the part, and that was the equation that we built after the history match. And we all know that the mass transfer is kind of slower than the temperature transfer. So there were certain interfacial tension reduction effects as well because of the mobility of the capillary trapped oil. And then we also see there's a development of oil bank near to the producer as well. And after history matching, we quantified the recovery factor, that we saw that almost 10% of the recovery factor is increased based on the history match of the 1D model, and almost 12% of the oil swelled based on the reaction kinetics, and then approximately 70% of the oil viscosity is reduced through this method. And after that, we upscaled our 1D model to the 3D model, and we ran different sensitivities of urea injection at different intervals of time. We saw that we evaluated that when we are injecting the urea at initial phase of the life of the injection, we get higher and higher amount of incremental recovery. But when we because of the higher residence time of the urea inside the reservoir, but if we are injecting the urea at later part of time, we are getting some additional recovery, but that we are not allowing urea to get more and more time inside the reservoir and generate more and more CO2. And after that, we also evaluated that when we are injecting water initially, we are actually creating a cold bank near to the injector area. And after that, when we are injecting the urea into that similar injector, that urea is not going to react because of the colder bank near to the injector area. And so that's why we recommend that in order to rather than injecting cold water, we inject similar produced water inside the reservoir to actually reduce that colder bank near to the injector area. And also we sensitize some amount of urea that in order to optimize the cost of the injection of the urea. So we got the optimized results at almost 15% of the urea concentration that we injected. And also we use the real time or the real field PVT data and the geology data, but we did not use the structure of the data for this study. And after that, we ran some sensitivity analysis by utilizing the objective functions and some artificial intelligence as well. And we evaluated that almost like at 240 degrees Celsius, 2 degree Fahrenheit, we get the maximum result. But after that, our recovery doesn't increase. Rather, also we are increasing the reservoir temperature as well. So basically, it gives us the temperature envelope for this method. So initially, we evaluated this 70 degrees Celsius from the Gibbs-free energy, and after that, from the modeling, we are getting this 240 degree Fahrenheit as a maximum temperature for this viscosity of the oil. And also we evaluated that the almost 90% of the CO2 that is generated in the reservoir, it is dissolved into the oil. And another interesting fact was that when we modeled that 3D quarter 5 spot model, we saw that the majority of the CO2 that is generated in the reservoir is partitioned into the heavier components of the oil, because in the EOS system we divided our oil into 3 components, into the lighter components, medium components, and the heavier components, and in order to see where we have the major viscosity changes and major oil swelling for this through the in-situ CO2 generation. And we saw that we got the majority of the CO2 it is going to partition into the heavier components, and it gives us more and more recovery of the heavier components rather than the lighter components. So these are the key outcomes. We saw that the temperature envelope is mainly between the 270 degree and the 240 degrees Fahrenheit. the CO2 partitioning into the heavier component is another interesting outcome from this study, because it is going to help recover more oil from the heavier oil or the medium oils rather than from the lighter oils. And also we can utilize the produced water for injection purpose rather than the cold water, in order to have more and more impact of the urea generation because of this temperature effects. Also there is another recommendation from this study, is that if anybody wants to work on this, he can try this CO2 partitioning under different rock types, because we did not evaluated the heterogeneity and the different permeability or the different rock units for this method, and also different oil composition. This method should be tested under different oil composition. Although it gives us the results for the heavier components, but we should try it for the different oil composition in order to get this result, whether this technique should be applied on the variety of the reservoirs or not. In the end, I would like to acknowledge and thank UP management for allowing me to present and publish this work. And these are the references that are used in this study. And thank you,
Thanks, Saddam, for nice presentation. Now the forum is open for questions. We can accommodate only 2 questions.
Thank you very much. My name is Munib Virk from Mari Petroleum. Nice presentation, nice work. Just a few questions regarding this. Do you have any actual field case study where this technology was applied?
Yes, there are
first question. Just let me 2 or 3 questions.
Okay.
Quick questions. The second question is, when you inject urea, after the reaction with water, how you are tackling the change in the mobility of water as well, and the change in the relative permeabilities because of the change in the nature of water, and its impact because of the water salinity, if there is any. And thirdly, have you considered the minimum miscibility pressures of the CO2 into your oil phase? Into the simulation, have you considered that as well?
Yes, starting with your first question was about the field case studies. Yes, there are some field case studies that are ongoing in US and in China as well, because this technique is mostly applicable to the water stripper wells that are producing at around 90 and more than 99% water cut, and they are converting into the injectors and injecting urea and getting more and more oil after that. There are some case studies available, and there are some recently published some case studies as well. I forgot to mention the paper number, so I can give you the paper number as well. After that, the second was about the urea, the salinity. Okay, so it doesn't change the water mobility so much, because this urea it's when we are injecting along with the water, it doesn't act like a polymer, because it doesn't have more heavier components into the urea. It just it's in the liquid phase, and once it contact with the reservoir and have the temperature effect, it's going to decompose into the CO2 and into the ammonia. So it doesn't have more time in order to actually reside into the reservoir or adsorb into the reservoir. But we need to check under different permeability conditions, that if there is a permeability is very low, so there will be challenge in order to actually pushing the urea solution into the reservoir and have this reaction activated. And third question was about the salinity. Yeah, miscibility. For our case, we kept the injection pressures above minimum miscibility. We computed the minimum miscibility pressure through equation of state. We had the laboratory tests available for the oil, and we developed equation of state model and computed the minimum miscibility pressure by injecting or by mixing different CO2 mole fraction and kind of evaluating where we have the maximum CO2 mole fraction injected and where we have the maximum oil swelling, and that we kept at the minimum miscibility pressure, and we kept our injection pressure above minimum miscibility pressure.
Saddam, nice work. You mentioned in your slides that reduction of interfacial tension.
Yes.
So have you calculated value of interfacial tension which you get after injection of urea?
So since it was, we did not have the validation from the laboratory methods. So in the laboratory, it gives us the overall recovery. Okay, so we are getting 10% more recovery or 15% more recovery, but it doesn't quantify how much it is from the oil swelling, how much it is from the interfacial tension. So we during our 1D history match model, we kind of iterated this this interfacial tension by changing the relative permeability endpoints and getting the history match, get better history match. But there is for sure there is an interfacial tension effects as well, because if we are not changing the relative permeability endpoints, we are not getting this much of recovery. So yes.
Yeah, thank you. One more question. You in your slides you mentioned that after 70 degree centigrade that reaction becomes rigorous.
Yeah, spontaneous.
Fast, spontaneous. Yes. So you also mentioned the temperature graph with it. So does this mean that you have also injected the optimum amount of urea in reservoir? Because after some temperature 240, 250 degree, the recovery becomes constant.
Yes.
So this means that that's the benchmark in which at which you injected volume of urea as well.
So we, for the 3D case, when we ran different sensitivities on the urea concentration, we got the optimum result with 15%. If we are injecting more urea, actually we are increasing the cost of the project, because urea it costs around like it is around $3 per pound of the urea is the cost. So if we are injecting more and more urea, but that is particularly for this viscosity oil, like I mentioned, that is for 3 centipoise oil. If we have more like viscous oil, then I think the urea concentration might be higher or lower, because for this case the viscosity of the heavier component in our equation of state was around 15 centipoise, and there was majority of the CO2 that was generated, it partitions into the heavier component. So we see that this technique is more effective for the medium to heavier oils.
Okay, thanks, Saddam. I
Thank
think
you.
Mohsen can engage, Saddam in lunch time. Time is running short. I think we should go ahead.
Thank you, everyone.
Thank you, Saddam. It's very interesting work, I think. I hope this can find some practical application within local industry. I have a few questions I'll ask you offline. So the next paper is on improvement in drilling efficiencies by using mechanical thruster in BHA and long gauge bit. And this is being presented by Humaid Muiz.
Assalamu alaikum and ladies and gentlemen. So let's start with the improvement in drilling efficiency by using the mechanical thruster. So unleashing the drilling prowess. In this presentation, we will discuss about how the technological advancement pushing the dynamics of the drilling engineering. So as we all know that the drilling operation is one of the critical operation lively going on, and the people's hierarchy from higher management to lower management putting the keen interest about every second updates. So sometimes the frustrations arrive of the low ROP, high stick and slip, high torque and unwelcome vibrations, which ultimately add the negative energy inside the string. So in order to mitigate those energies, we have introduced this tool inside the BHA to overcome those challenges and provides the desired results. Could you please move on? So secondly, I would acknowledge the authors and the co-authors of this paper and their valuable contribution to shape this paper to present it in this forum. On the left side, we can see there is a Cougar team, and on the right side, the Mole Pakistan teams. So their valuable time is appreciated to shape this paper to present it in this forum. Please move on to next. This entire presentation was structured around the following points. First, we would discuss about the introduction to the case studies. Secondly, we discuss about its schematic. Afterwards, we move on to its features, that how this tool works. And fourth, we move on to the placement analysis, that through working out some simulation, how can we place this tool inside the BHA for taking out its maximum efficiency. Then move on to some observations, and finally the results and conclusion. Next. So starting with the case history of this well, Mole well has been drilled Tarnaul 1 in 2022, Margla block, Pakistan. So drilling of Murray formation in 12 1/4 inch section, which compromising of interbedded lithologies, such the stingers of siltstone with sandstone in the massive clay stone. So what we have observed that the reduction of ROP and the increase in the stick slip. Multiple trips has been conducted with various bit types, but no improvement. As we can see, total 3 trips drilled from 625 to 3,600 meter with different parameters and applications. Obviously, there are some aggressive bits have been utilized. The 519 bits, the steel body bits, those are usually aggressive bits in this case, but ultimately the result is on the compromising side. So what the solution come up with us, the Mole team has delegate and strike their thoughts and their brainstorming that how could to mitigate this kind of vibrations and stick and slip issues. So while working on extreme side, we come up with the solution to deploy this tool inside the BHA so that we can reduce this with the weight on bit, optimizing with the weight on bit and reduces the vibration at the over to pertaining a good ROP with the required strategy and interval. So before deploying it onto the BHA, there are some risk analysis has also been done, in which we have we collectively discussed with the Cougar team regarding its torque limits, their pressure drops issues, their through bore ID of the tool, and it's if we are applying a jarring, so what kind of effect it can be seen. So overall the effects on the lower side, and further while discussing with its working principle and tool, I think Humaid will further discuss and gives you detail about the tool and its working principle. So Humaid, can you please? Thank you.
Okay, so this is a schematic of the mechanical thruster. Simple sort of tool, nothing very complex about this. The main thing where this tool, the main feature of the tool is in here in the spring stack. If you can see in the spring housing, that's where this is configurable, and this is what actually balances the compression against the pump open force or the differential pressure that is produced downwards. So once we apply weight on bit from the top, what happens is that the male spline compresses the spring assembly, the spring housing, the spring assembly which is in spring housing. The spring housing has to actually balance itself, balance the weight on bit with the differential pressure which is produced below the tool on the bit. And resultantly, what happens is that as a result of this compensation, a consistent amount of weight on bit is applied on the bottom, and that produces that actually reduces the vibrations, and it also results in improvement in the efficiency of the drilling operations. There is one last part of the piston sub, just a simple compensation piston, and the function of that is to have sufficient lubrication to the spring assembly so that the springs do not get heated up and get failed. So that is just a simple schematic of the mechanical thruster. These are the features. So there are three forces that are acting on the tool when it is downhole. One is the compression, or the weight on bit. Then comes the pressure drop or the differential pressure, the pump open force that occurs below the mechanical thruster in the BHA. And the third one is the weight of the BHA that is below the mechanical thruster. All the components that are below the mechanical thruster, their combined weight. So these are the three forces that act. And all these three forces, these are balanced out by the mechanical thruster, by the spring assembly of the mechanical thruster to provide a consistent force to the bit at all times. The vibration mitigation, as a result of continuous force to the bit, what happens is that the axial vibrations and any stick slip that is produced by the bit, that is reduced, that is mitigated. So what the mechanical thruster does is that even if the stick slip is there, it will reduce any triggering of the stick slip to a certain level where drilling has to be stopped. So that's where this vibration mitigation feature of the mechanical thruster comes in. The mechanical thruster is configurable as per requirement. The spring assembly that is customizable as per the requirement, as per the BHA. It can be run with the RSS BHA, with mud motor BHA, any range of parameters. We can set the mechanical thruster springs in such a way to cater for the parameters in which it has to be used. The mechanical thruster, by design, it is double thrust motion, upwards and downwards. So 12 inches of downwards and 12 inches of upwards deflection, it exists in this tool. So, there is a double motion of both up and down. It's a through bore ID. There is very low pressure drop across the tool. The other thing, through bore ID, the spring assembly, which is the main part of the thruster, that is completely separated from the drilling fluids. So any type of fluid, LCM, any sand content, any solid amount, any mud weight, that is not going to affect the functionality of the tool, because the spring assembly is completely separated from the fluids. It doesn't come in touch with that. So any LCM want to pump in case of losses, that can be pumped. Even if an intervention is required, so that is also possible because the tool has enough ID. The tool, up till now, it has more than 6,000 runs across the globe. First, it was used in North America. Even now, that is the largest market for this tool. Since this case study, which was the first time we used a mechanical thruster in Pakistan, we have used it with more clients as well. And there is a very low failure rate. Just maybe 2 or 3 failures that have occurred. The other thing is that even if the spring assembly fails during the operation, it is not going to affect the actual operation that is happening at that moment. So no trip is required in case the spring assembly fails. Before running the mechanical thruster, we perform its placement analysis in regards to the proposed BHA and the parameters. This placement analysis is for specific this case study. So what we do is we put the mechanical thruster inside the BHA. The client provides us the parameters, the weight on weights, the pressure drops that are occurring below the tool. We put all of that data. We put the mud weight. We put the inclination that is there. And as a result, the other graph on that side, that shows us where the performance of the mechanical thruster is going to lie. So if the performance, if the curve is in between the limits of the mechanical thruster, the mechanical thruster spring assembly, so it's going to perform optimally. And that tells us that, okay, we can run this optimally and it will perform as per requirements. So this was the placement analysis that was run for this case study. And for every run, for every job, the placement analysis is run. And we cater it for as per the BHA and the parameter requirements. These were some of the case observations of this Ternol 1 drilled by MOL. So what we did was that we compared actually the runs in which mechanical thruster was involved and those in which there was no mechanical thruster. So since Azim actually mentioned that they were having an interbedded zone where there were stingers of siltstone embedded with clay and sand. So before the application of mechanical thruster, there was a lot of invisible lost time. Whenever there was a stick slip encountered, the BHE needed to be picked up, and then there was quite considerable time that was spent in reducing the stick slip and then tagging the bottom again. So with mechanical thruster, there was a reduction in invisible lost time. The vibrations were also reduced in the interbedded zone while using steel bladed long gauge PDC bit, which is an aggressive bit. The weight on bit application was good whenever weight on bit was required as per the formation drilled. So better weight on bit application was possible as compared to the runs that were previously performed without the mechanical thruster. The other thing that the steel body bit, it was an aggressive bit, 519 PDC. So it was expected that it might provide a better ROP, but the vibrations will also be there. But with the addition of mechanical thruster, it was quite efficient, and the remaining section was drilled quite efficiently. So these were some of the observations of the case. This is the post-job analysis. I will explain just briefly. The section started from 2148, 2150 meters. Up till 2948 meters, the performance was quite good. There were no limitations on the GPM or pressure limitations. After this 2950 meters depth, they started to get the interbedded zone with stingers of siltstone and claystone. And from 2948 meters up to 3600 meters roundabout, that is the zone where they tried to drill it with different parameters, different bits, but there was a reduction in the ROP. There was also a lot of erratic torque that was observed during this phase. The last phase from 3600 meters up till the end, that is when the mechanical thruster was added. So there was an improvement in the ROP that was observed overall if we compare all the intervals actually. Similarly, the weight on bit application as per requirement, that was better because prior to the mechanical thruster, they tried to increase weight on bit, as you can see in the upper portion, but in the interbedded zone. But they faced a lot of stick slip, so they had to keep it down. And similarly, the stick slip, they sort of remained almost the same, but considering that the steel-bladed aggressive bit was used with the mechanical thruster, so the vibrations were almost similar. So because of the mechanical thruster, we have this advantage. This was the final result. We compared the runs. Prior to mechanical thruster, the average ROP was 4.3 meter per hour. With mechanical thruster in the 3 runs, the average ROP was 5.9 meters per hour. So percentage-wise, there was a 37% improvement in the ROP. Final conclusion: the vibrations were mitigated with the enhancement of ROP, and this also allowed the application of aggressive bits to drill hard and interbedded zones with much better efficiency. That is all from us. If there are any questions, please.
Thanks, gentlemen, for question session. I think time is short. We are really sorry. So we can accommodate only 2 questions.
First of all, very nice presentation. Farhan from PPL.
Thank you.
My question is regarding what are the surface indication of failure of these thruster. And in terms of money, how much you saved by utilizing this tool?
On the surface, if there is a failure, just like I mentioned, it is not going to hinder the operation that is going on. But what we can feel on the surface is that the vibration log, that is not going to be the same when while the thruster was performing. So that can be one indication which we can get from the real-time MWD logs. We can see a difference there. As for the improvement in the, can you comment on this, please?
Yes, as part of the ROP concerns, if you increase with the ROP, so ultimately the section which you are going to drill in 4 days, you can able to drill with the lower stick slip and vibrations, you can able to drill in 2 days. So you can overall see the impact of cost there. Ultimately the services, rig time, all are the saviors for you.
Any more questions, please?
Mr. Humayt, it's very good technology, mechanical thruster.
Thank
How can you relate it with the AST, anti-stalling technology? So if we compare both these two technologies, which one is good?
There are some tools that are used for the vibration mitigation. Other tools, they are on the market. But what I can compare with is that there is a tool, for example, by a company Tomax. Tomax is actually the same, that is the this stick slip tool, but they have a little limitation regarding when it comes to the mud properties, because our tool is completely separated. The spring stack, which is the main part of the tool, that is separated from the fluids. The AST tool, that has some limitations there. It cannot work with more than 1% sand. And similarly, there are some solid constraints and mud weight constraints with that. So there is a comparison with that. The other thing is that we have a 24-inch deflection up and down, 12 inches down, 12 inches up. Their tool is single acting, and that has a 7.2 inches deflection. So ours is more flexible, and it's both ways.
So you said that there is a separate path for drilling fluid in the BHA.
No, actually, if in the schematic, the spring assembly, which actually compresses or which balances itself with the pump open force, that is housed inside a certain spring housing, and that is completely enclosed, and no drilling fluid can go inside and affect it. So there is no effect of any type of mud fluid on the spring assembly. So it is not going to be affected.
Thank you.
Thank you, gentlemen.
Thank you
very much.
Thank you so much.
Thanks for nice.
All right, the last paper for the evening is Successful Integration of Channel Fracturing Unveils Promising Prospects in the Southern Region of Pakistan. It will be presented by Haris Ahmed Siddiqui.
Thank you. I may start. Okay. Good afternoon, ladies and gents. First of all, I'd like to thank the chairman, co-chairman, and all the ATC members present here for allowing me to present this paper. My name is Haris Ahmed Siddiqui, and I am representing SLB. So the topic today for the presentation of my paper is successful integration of channeled hydraulic fracturing, which unveils promising prospects in the southern region of Pakistan. This is basically a case study from Pakistan, including the 3 partners, mainly OGDCL and SLB, and then some JV partners from KUFPEC. Thank you. Let me go through the agenda today. So in my presentation today, I would go through the project overview, the challenges that we have and how basically we encountered and what solution we have proposed, including the phase strategy. And then finally, I would conclude my presentation by giving you guys the conclusion and the results, as well as the way forward. Starting with the project overview, as we all know that Oil and Gas Development Company is one of the largest E&B in Pakistan, holding 75% of the interest. This is a case study of the second largest field after Sui, which is the second largest gas field, where we have the prospects to go through the candidate selection phase of a stimulation or the production enhancement. Basically, the stimulation technique of acidizing is already in place in this field. This is an old field which started and discovered back in 1990. And then there were multiple things that were going on this field to improve the production of the wells, while the hydraulic fracturing was unexplored or untapped in this field. So once we started to work on the candidate selection phase to come up with a production enhancement part, we started analyzing the old wells that were already being stimulated using the acidizing technique. But the main challenge here was to understand that and to have a sustained production for a longer period of time for this field. Then the two main options came into play, which are the acid fracturing and the propant fracturing. This is a carbonate formation, this is a limestone. Basically, moving forward, the comparison of the two technique and how we came up with the final decision of evaluating these for the propant fracturing. The main two key parameters to differentiate between the acid and prop are basically the leak off and the longer length of the hydraulic fracturing. These are the two main points which were considered, and then based on the stresses that we experienced in this field, which I would discuss in detail in my next slide in the technical part, that the stress is higher than 5000 psi. So the breakdown pressures here are higher, which makes acid fracturing a less feasible option compared to the propant fracturing. So three main candidates were analyzed, and then one of the candidate with respect to the execution part as well was feasible and proposed to go ahead as a pilot well and to see how the propant fracturing will act on this well. The main challenges that we faced were numerous, as this was the first pilot well that we are going to do it with the hydraulic fracturing part. Some of them are highlighted here, which include the absence of stress barriers, which is one of the major thing in terms of frag containment. So basically, the frag height is dependent on the stress barriers that we experience. Then the frag gradient ranges. Frag gradient basically ranges here from 0.73 psi per foot to 0.89 psi per foot. The breakdown pressures were a bit higher, so basically the objective of the well is not drilled to the frag. So the completions were not mainly designed to contain these high pressures. So this is another challenge to propose hydraulic fracturing on this well. Which was taken into consideration during the candidate selection and ranking phase. And then lastly, the last thing is the completion quality. So we need to see how is our completion, how old is it, and will it be able to sustain the fracturing pressures that we are targeting. So as a solution, we proposed integrated workflow of 5-phase strategy. This include the feasibility study. In the feasibility study, it started with the construction of mechanical earth model, frag design, and then finally the production forecasting phase. So with the joint meeting, with the mutual discussion between all the partners and the shareholders that were involved in this project, we finally mutually agreed on the way forward and started with this integrated workflow. The first thing that we did was to come up with a feasibility study, which includes the construction of 1D MEM, which is the mechanical earth model. The main objective once to construct the MEM is to understand the stresses that we have in this area, to understand the rock mechanical properties like Young modulus, Poisson's ratio, and to have the overview of the pore pressure over the different layers of the formation, and how our fracture design will propagate. The second phase after doing the MEM part in this feasibility study is basically the frag design, which is the frag simulations. So in simulations, the main points that we are considering is basically the frag conductivity, and then the frag geometry, which is the frag height, frag width, and frag length. Finally, the third phase of our feasibility study is the production forecasting part, where we developed a simpler model, where we did the history matching of the well with all the production data that was available for this well, and we came up with pre-frag and post-frag profiles to showcase to all the partners that what we are going to do and what will be the result of this feasibility or the proposal of hydraulic fracturing. Finally, we presented the recommendation of this analysis and the feasibility study to all our partners who are involved, and then we mutually agreed on the way forward to let's do the hydraulic fracturing part and see how it proposed. So initially, due to the challenges with respect to the confidence on the technical data, this was the first proposed well. We proposed to go with the breakdown injection part and the data frac to understand the technical parameters and the technical reservoir parameters, and then once we have the confidence on that one, we based on the analysis of the data frac, we move forward to the execution of the main job. You know, the fluid is one of the major component of hydraulic fracturing part where the lab testing comes into play. So the comprehensive lab testing was performed on whatever fluid is going to be pumped inside the formation and how will it be react. We have our district lab where we do the complete lab testing, and here you can see is basically the viscosity of the well doing the actual HPHT conditions on surface and understanding how our fluid will react with respect to the bottom hole conditions. Temperature log was recommended, basically the before and after the injection and the data frac part. This is to understand the frac height. Basically, since we have the absence of stress barriers, as I mentioned in one of the major challenges, so temperature log acted as to understand like how the fracture is propagating and what is our frac height. So here we saw that the fracture height was growing inside the inside the formation, target formation layers. So basically this is helping us with respect to the production enhancement part in terms of sustainability. So this challenge was addressed in this way. Finally, we have performed the breakdown injection and the data frac, and the results were similar to what we had designed or what we have simulated in the feasibility study part, which is the closure gradient, the fluid efficiency, which we got was around 35 to 40% for the fluid. We somehow experienced the high height growth, and this is in line with our temperature log that we have found. But the good thing here for us to mitigate this challenge is that it's growing inside the layers which are in our target, and we don't have any water zone nearby on that part. Finally, we redesigned the well based on the analysis and that we got from the data frac, and we pumped the main frac without any issues. The total propellant that was placed inside the formation was 122,000 pounds of propellant with the maximum PPA in formation of 6 PPA. So that's how basically it was achieved, and the job was successfully and flawlessly executed, finally giving us the successful results in terms of production enhancement. So this well is producing from the last 6 months as expected, as per our expectation in the feasibility study production forecast, and this had given us around more than 2-fold of increase in terms of production enhancement. So this proved to be one of the successful cases of hydraulic propellant fracturing in the carbonate limestone formation in this second largest gas field of Pakistan, which was earlier untapped with respect to the propellant fracturing. Finally, I would like to conclude my presentation by giving the final basically thing on the approach or the strategical workflow that was adopted here in terms of the integration. So basically a multidisciplinary team was there, which include the reservoir engineers, the production engineers, and the hydraulic fracturing engineers. Starting with the integrated approach, sitting together with the partners, we improved the workflow, starting with the feasibility study, then different proposals on the data frac part, and then finally the execution of the main job, which proved to be a success for us. So these are some of the major elements, the improved workflow, and then finally the implementation of this technique. As a result, we implemented here was the technology that we have used is the channel fracturing, compared to the conventional, we have the higher operational efficiency. We have the higher conductivity flow channel because this technique involves the pulsation parts, where our fluid is optimized, and then because of the pulsation, we have certain other benefits over the conventional technique that is already being used globally. The placement rate in terms of screen out is better because of the pulsation and the drop in the hydrostatic in the column. And then as per the results, it's a better technology in terms of production enhancement as well, which is proven by the results that we have. Thank you.
Thanks, Haris. Floor is open for questions. We can accommodate 3 questions. The time is short, so please go ahead. Applause.
Thank you, Haris, for presenting and sharing the case study for this, the first pilot project well in Kadarpur field. My question is related to your conclusions. As you have stated that this well has been put on production for the last 6 months and 2-fold production. But what's the way forward for this well? So do we have to repeat the frac job in this well at after a particular interval, or seeing some parameters that has, if we see deterioration, or we have to repeat this frac job, or we have to go to conventional matrix stimulation for sustaining the production from this well? Thank you.
Thank you, Frasab. Very good question. So from the sustainability point of view, that's the main objective. So hydraulic fracturing, as we are aware that it's a quite basically the life of hydraulic fracturing is quite a longer period of time. So at the moment we need to understand the well, that how we quantify what damage are we experiencing. So basically for this field specifically, if we see that the production is going below par or whatever line we have set, then we can do the acidizing part to do the perforation wash to connect, or if there is any damage on the near wellbore part, we can remove that in that way. But this would obviously be a better option compared to the matrix acidizing that was being done previously on this field. Thank you.
Shah Jahan from Mol, Pakistan. You mentioned that there was not much stress contrast in the target zone. So was there any stress contrast available for the above formation, for example SUL and Ghazij, so that the height of the fracture can be constrained? And since the height of the fracture was quite much, so how did it impact on the fracture half length, and was there any impact on the productivity? Thank you.
Thank you, Shahjahan sir. Very good question. I was expecting this question. So basically, when we did the feasibility study, as I already mentioned, that this was one of the challenges that we faced, that there are no stress barrier. But the good thing here, which supported our case for hydraulic fracturing, is that the upper and lower, basically we have slightly higher contrast, which is basically stopping our fracture to grow over the target formation zone. So that's the best part here, which makes this candidate well a feasible option for the hydraulic fracturing. Now the second part, how does it impact the frac conductivity? For sure it is impacting our frac conductivity, because the height, basically in hydraulic fracturing the main challenge is to control the height. And then this is one of the major challenge in this field because of the absence of contrast or the lower stresses that we experience. But basically this is the part where I mentioned in my presentation that we basically sit together with all the partners and showcase them that with this frac, with the simulation, we came up with the frac conductivity. So we have the frac conductivity that we are proposing in our design. With respect to this, considering all these challenges that we have. Based on that, the production forecasting was done, and then the results were agreed that, okay, fine, we are good to go with this one. This will vary, obviously, in this field for different candidates, well to well, but more or less, we will experience the similar kind of behavior if the stress barriers are absent somehow. Then there are, I mean, the technique implemented here was there was the cost optimization part as well. So we don't have the option to go to the workover rig. If we have the option to go to the workover rig, we have other mechanical options available. Thank you.
Okay, thank you very much. It's a very good presentation, and it has given us some good understanding about the fracture in vertical well. But I feel that this productivity is not as much as encouraged, you know. Unfortunately, fortunately, when people are doing fracturing, if the well was producing 1 million and it has produced after fracturing 1.5 million, there's a 50% increase. In absolute terms, the increase is not too much, you know, about 1 million or 1.5 million is producing now after fracking, after this technique. My recommendation to the Kadarpur field, and we will discuss probably, that this has given us information about fracture conductivity and breakdown, all other parameters. We should be doing a horizontal well and doing a set of frac job to increase production by 2 or 3, 4 times. So this well has given us indication that yes, the rock can be frackable, but horizontal well is the only solution here to produce a maximum gas from these tight reservoirs. So horizontal well should be designed, and fracking feasibility should be done on that wells rather than doing a vertical frac job, which is not encouraging. You know, we want to increase from 170 to 270. The gas is there in Kadarpur. The only way is to do the horizontal well and then frac.
Thank you, sir. I would take it as a comment, and to add on that part, I do agree that obviously horizontal well have no comparison with the vertical well in terms of the reservoir contact area. So for sure, but the challenge, as I have mentioned, that this is an old field and these wells are not drilled to frac. So we have a challenge in terms of completions, quality, and the frac propagation part. So with all these challenges, basically, we come up with this optimized candidate well. Thank you.
Haris? Very quick question, please.
Yes, very quick question. First, thank you very much for a very good presentation. I think I should commend you that limestone fracturing with proppant has been around for quite a few years, but in Pakistan, people have not tried it. And I think you have broken a mental barrier here, so I must congratulate you for that. My two questions, I have two questions, very short ones. One is about the proppant flowback. After you did you see any proppant flowback, and how did you manage it? That's number one. And then the second thing is, which is actually Dr. Saab's comment, it's just related to that as well, that the incremental cost and incremental production, how does the payback time work according to the incremental cost that you did because of incurred due to the frac, and then you had incremental production on the later? Thank you very much.
Thank you, Irfan sir. So basically, on your first question, yes, I do agree that in limestone there are some cases, but we don't see much success in the proppant fracturing part. But yes, as our objective was to have the sustainable production, so basically this was the option that was available. And then from the cost point of view, in terms of cost optimization, basically here we didn't went for any workover part for specifically to this case study that I have presented. So that was one of the good point for us, for all of us, that our costs were optimized in that part, that we don't need to bring the workover rig, or the workover cost is saved in terms of that. And we did whatever was there. Basically this well was a very low producer and it was not going into the system, but now alhamdulillah it is producing well compared to the initial thing that it has. So that was the major point to present here in this, that from nothing it went to something. For sure, to give it sustainable and things like that, we have other options to consider, and then comment on that one, discussing it with all the partners, like how and what we can do on that part. Your second question regarding how we basically incorporated. So we sit together and we perform the economic analysis based on that, like what cost we are putting in this. Like without the workover, it's a relatively lower cost compared to the wells or the other candidate wells where we need to perform the different workover options like perforations or closing some perforations and then reperforations or some other method. So from that point of view, we sit together and we basically discussed with OGDCL and partners that how is it benefiting for us. And after agreement on that part, we went to do this. So that was in consideration.
Thanks, Aris.
Thank
you very much. Thanks for the time.
Thank you.
So with this presentation, it's the end of presentation sessions. From this session of today, it's time to pay a little tribute as a token of appreciation to all the authors and co-authors for their hard work. Shields will be presented in a line with the pattern the papers were presented in this session. So the first paper presented in the session 2 for today is High Rate, High Volume, a novel technique for uniform metric stimulation of naturally fractured low pressure reservoir. Mr. Harun Rashid presented the paper, so I will request Mr. Harun Rashid to please come forward and receive the shields. Arif Yusuf, Ghulam Muhammad Waqas, Salim Saeed, and Jazeb Ali Bukti. In case of absence of all the co-authors, I will request the presenter to please collect the shields for them. The second paper presented today was from United Energy Pakistan Limited. Paper holds the title of Role of Temperature on the Performance of In Situ CO2 and Hand Soil Recovery. Paper was presented by Mr. Saddam Hussain. I will request Mr. Saddam Hussain to please come forward on stage. Zahir Ahmed, Mutafadil Murtaza Zakir, and Muniz Iqbal. The third paper presented was Improvement in Drilling Efficiency by Using Mechanical Thruster in BHA and Long Gauge Bit, a Case Study. Papers were presented by Humaid Moiz. I would request Mr. Humaid Moiz please come forward on stage. Shah Jahan Khan, Mohammad Asim, Zaman Sarfaraz, Waqasuddin. The last paper concluding this session was Successful Integration of Channel Fracturing Unveils Promising Prospect in the Southern Region of Pakistan. Papers were presented by Schlumberger Pakistan. I would request Haris Ahmed Siddiqui to please come forward and receive his shield. Syed Afraz Haider, Syed Ali Hasnan, Mohammad Sadiq Bal, and Nasir Hamim. After presenting shields to the authors and co-authors, now it's time to pay a little tribute to the chairman and the co-chair for the session today. For this, I would like to request Dr. Huram Zahoor to please come forward on stage and present the shields to the authors, chairs and the co-chair. The session was chaired by chair and co-chair by Mr. The session was co-chaired by Mr. Fahim Raza Kawan. So with this, we end the entire two-day session for the technical paper presentations. I would like to thank all the authors and co-authors for their hard work and presenting papers here. We'll also be thankful and I'm really grateful to all the audience for being so humble and sitting over here. Signing off from this session, Seher Malik.